Let me know when it starts. Oh. It's a bit bright here. How about that? That's a bit better, right? Okay, good. Cool. I think we can get started. Okay, so we're nearing the end of the lectures. Today we're going to talk about interconnects, which is really a fundamental topic in essentially everything we talked about so far. But just as a reminder, what we got here recently was we talked about multiprocessing, memory ordering, and cache coherence yesterday. These are all very fundamental and important topics, and clearly they have a lot of implications on the systems we build today. But hopefully it's clear to you that a lot of this is all about, again, memory, right? We talk a lot about memory systems, even when we talk about multiprocessors. So that's an interesting thing to consider. And today we're going to talk more about memory systems and communication, which is interconnects. Let's see, this is still not working. Yeah, there's communication issues, as you can see. Okay, better. So recall from yesterday that we covered cache coherence. We went into somewhat detail on some topics, but there were two major approaches to cache coherence. One is Snoopy bus, and the other is directory. And we said that Snoopy bus is not so scalable. There's a single point of serialization for all memory requests, whereas in directory, there's a single point of serialization per block. So it's a bit more scalable because of that property. And then we discussed the trade-offs. I will not go into all of these details, but directory essentially adds indirection. So the latency is longer. Snoopy cache, Snoopy bus doesn't have that indirection. But as we discussed, there's a single point of serialization, which requires some sort of a bus or a virtual bus or totally ordered interconnects. So we kind of discussed interconnects, but we didn't go into that as much. Today, we're going to go into interconnects because interconnect really determines the scalability of systems that we build today. It also determines the latency of the systems that we build, as we will see. And we said that directory is much more scalable. It's in fact exactly as scalable as interconnect and directory storage. We talked about directory storage yesterday. We saw how big the directory was actually. And that's one downside of directory-based systems. But now we're going to talk about interconnect and see what kind of interconnects can enable scaling better. Does that sound good? Okay. I guess I should really avoid using this. Okay, so that's what we're going to talk about, essentially. There are a bunch of readings. I'm going to cover some of these. Tomorrow, well, I guess next week, we're going to cover some others. Let's see. Today, we may not be able to cover all of these, actually. A lot of these are related to on-chip interconnects. But we will talk about especially the last two in not so great detail, but these are some of the fundamental papers in interconnects. As you can see, one is from 1979. Okay, let's start with the basics. So what is an interconnect? Essentially, interconnect is, you can think of that as anything that's used to connect and communicate components. These are a set of wires and a bunch of other things that make the wires work, enable the communication and connection between the components. That's how I like to think about it. At the fundamental level, it boils down to some sort of wires. Of course, there's wireless interconnects also. More recently, those are also communication methods. So those are also part of the interconnection network today. So it doesn't even need to have wires if you think about it. That's why I defined as anything that's used to connect and communicate between components. So this definition is actually very fundamental. It doesn't even assume wires, right? So there are many examples. Processors and you might want to connect processors and processors like in multiprocessor systems. Processors and memories, different banks. Processors and caches like we did yesterday. Caches and caches like we also did yesterday. And I/O devices as well. So it could look like this. This is one sort of multiprocessor system. You have CPU, memory, some sort of network controller, and even a disk. So these are different machines, and there's interconnection network. This is essentially a network today, right? It's a network-based multiprocessor. So we're going to look at a lot of these pictures today. So these are a couple of pictures from a paper that's will be in your reading list in the next homework. It's a very fundamental paper on message passing computers. But you can see that there are different organizations that you can have. For example, here, you can have processors on one end, and then storage modules, memory banks, you can think of it that way, on another end. And there could be a network between them such that any processor can access any storage module, right? You can think of it as a bank, as I said, memory bank, for example. But it could be something else also. It could be really an SSD device, a bunch of SSDs over here. But traditionally, supercomputers kind of looked like this. You had many processors and many memories, and then they got connected to each other with a switching network. And we're going to examine this structure. But we're also going to examine this structure. Which looks more like processing and storage are together. And then you connect each of these combined modules in some way using some interconnection network. In this case, it's a three-dimensional hypercube. We will see six-dimensional hypercubes later on, which is essentially the cosmic cube paper that is proposed in the 1980s discusses. Okay, so why is this important? Before we go into so this is an example of organization and topology. This is one topology, how you connect components. Before we go into a lot of characteristics of this, there's not just topology, there's buffering, flow control, and routing that we will examine. But before we go into it, let's talk about why it's important. Clearly, how you connect things affects the scalability and cost of the system. How many wires you're using, for example. How fast you can actually access things. That's the second part, performance, energy efficiency. But scalability and cost means how large of a system can you build? Or can you actually add more processors without changing the system much, essentially? That's also important. It also affects performance and energy efficiency. How fast can processors, caches, memory units can communicate with each other? How long are the latencies between those units, or to memory, for example? And how much energy is spent on communication? So this is something that we have discussed earlier, actually, right? We discussed in processing and memory lectures very early on. We said that off-chip interconnects actually consume a lot of energy, and they also have long latency. So if you think about memory is a lot about interconnect as well. It's not just about the access latency to a given cell, but there's a lot of interconnect that you need to go through to get to the memory, right? You have to go through some on-chip interconnect to the memory controller. You have to go to some off-chip interconnect to the DRAM. And inside the DRAM, we looked at interconnects, right? If you think about the bit lines and word lines, they're all interconnects. They're all wires. And those wires are controlled somehow. And we discussed, for example, in tiered latency DRAM that reducing memory latency is about reducing the latency of the interconnect. But we cut the interconnect using isolation transistors. And those isolation transistors enabled some part of the memory to appear to have short bit lines, right? And those short bit lines enabled us to have low latency in that portion of memory. So if you think about it, memory is very tightly integrated with interconnect. And there was this discussion, I think it was an HPCA in 2002 or so, which is one of the major conferences. And the discussion was about, is it about the memory or the interconnect? I think I would argue that they're both the same thing in a sense, right? You use the interconnect to access memory or communicate. And memory itself is built using a lot of interconnect internally. So it's very hard to decouple interconnect and memory from each other. So it's important to really think about this a little bit more. Yeah, basically, a lot of the energy we spend, a lot of the performance we waste today is really about the interconnect. Of course, there are other things like we discussed, right? In adaptive latency DRAM, for example, we discussed that it's about the temperature, right? The timing margins. So that doesn't have much to do with interconnect, even though it's related. So there's latency that's not due to interconnect as well, but a lot of the latency is due to interconnect. Okay, so it also affects reliability and security, as you might imagine, right? We discussed this in parallel processing earlier. And one of the major reasons is, can you guarantee messages are delivered? What if the physical medium is very error prone and these wires have a lot of errors? How do you ensure that the network operates reliably and securely? And this is something that we're not going to cover a whole lot in these lectures, but you can imagine that during transmission across very long wires, there may be errors that are happening. There may be crosstalk between wires, and you need some protection for those errors. And there are a lot of methods that are used, like message checking, cyclic redundancy check, hashing, etc., to ensure that the message you delivered is actually preserves its integrity. So keep this in mind. We're not going to talk a lot about this in these lectures. We're going to mainly focus on the first part, scalability, cost, performance. Not so energy efficiency, but we will see that later on, tomorrow especially. Well, next week. I keep saying tomorrow, but hopefully you don't have a lecture tomorrow. Okay. So there are many parameters and goals. These are not just the only goals. So this is from a book that I will recommend later on. But basically, you can see that there's quality of service, reliability, availability, and then there are different parameters and properties of a network. I will not go through all of this, but you can also see that these major structures for communicating between processors and memory are similar to what we have discussed earlier in an earlier slide. But I would definitely recommend this book if you're interested in interconnection networks. We're going to cover interconnection networks in only 2 lectures, but this book is for an entire semester. You can see that there are 25 chapters talking about interconnection networks, and you can easily spend an entire semester, just like you would spend an entire semester on many, many topics that we have covered in these computer architecture lectures. So we're going to just go over this in 2 lectures, and even then, I mean, this book is relatively old right now. It doesn't cover a lot of the recent advances, for example. So we will cover some recent advances that are not in this book. Okay. So another example, which we're not going to cover necessarily, is the clock distribution network. We kind of talked about that in DDCA, Digital Design and Computer Architecture. How many people here have taken Digital Design and Computer Architecture? Just to show of hands. I guess those are the guys who are watching online. They're used to watching online. Yeah. Basically, if you've taken that course, we've covered this a little bit. This is another sort of interconnect. Basically, interconnects are everywhere. And you need to communicate, for example, the clock signal. Clock signal gets generated, and it basically determines the frequency of your processor. And then it gets divided across a distribution network. And the problem is this clock signal arrives non-uniformly late to different parts of a chip, right, causing potential timing issues. Ideally, you would like to have the signal arrive to all of the components at the same time so that you don't have what's called clock skew that we discussed in DDCA, for example. And the solution that people have developed is to design the interconnect, clock interconnect in this particular case, to equalize the arrival time of the clock signal to all parts of a chip. So you can see that this is a very specialized interconnect. And that specialized interconnect communicates the clock signal across the entire chip. And this is one example. This is an H-tree type of interconnect. You can see that it's like a tree. This is where the clock signal is generated or input. And then there's a lot of buffering. There's a hierarchical distribution network of the clock signal, as you can see. So the hope and the goal here is that each of these components that receive the clock signal and that use it for sequential logic receive the clock signal at the same time, right? So by doing enough buffering and equalization, hopefully you can get that. And you can read a lot of papers. There are a lot of papers that are written in the circuit community related to this. But yeah, this is just a slide from DDCA that we covered, I think, in lecture 8. Essentially, you need an intelligent clock network across a chip to keep clock skew at minimum. I said the goal earlier. So there are a bunch of different networks you can see. These are different network designs. It all starts with where the clock is generated. And usually there are like tree-like designs, as you can see in this particular case. It basically tries to equalize things. And they all have different trade-offs. So we will see that today also, except we're not going to specifically talk about clock. So my point here is that you can have specialized networks for special purposes. And this is a very specialized network that exists in existing chips so that the clock signal gets delivered around roughly at the same time. And you can see the skew distribution. This is from a real processor. This is alpha 21-264. You can read the paper. And this basically shows that given an H-tree type of network, tree network essentially, it's called H-tree. Well, let me go back to this design over here. This design is kind of called an H-tree. And they have an H-tree kind of network. And as a result, you can see the skew looks kind of like this, basically. This is skew, the difference in terms of the arrival time of the clock signal from one place to another place. Okay. And this is the lecture where we covered a lot of this, which I'm not going to go into. So if you're interested in timing and verification, you can brush up on the basics for sure. Okay, but now our goal is not that. Our goal is really the interconnection network basics. And a lot of these apply to the clock tree also, actually. But so we're going to cover a bunch of things. I'm going to define a bunch of terms. This is an area where a lot of terminology exists. So it's one of the areas in computer architecture and system design where terminology and jargon is a lot. I'll try to avoid a lot of terminology and jargon, but I will introduce some important ones. Topology is very important. Routing is very important. Buffering and flow control. is very important. These are basically three major things in an interconnection network, and we will see the importance. Basically, we will cover all of these in order. So topology essentially specifies the way switches are wired, and you have switches that basically switch that decide how a signal is routed. For example, we will see those also. So this affects everything essentially. Every metric is affected by the topology in the end, and we will see a lot of topologies. Whether you have a bus or a crossbar or some sort of mesh or some sort of hypercube, it affects all of your metrics in the end, including routing, including what kind of flow control may be possible, throughput, reliability, latency, and how easily you can build it also. Because in some cases, you will see that there are so many connections between the different components that you need lots of wiring resources to be able to build it. And those wiring resources may not be possible to have in different kind of chips, even in existing chips with lots of wiring capability, right? Okay, routing is essentially usually an algorithm, but it's also about design of the router. And the key here is that how does a message get from a source to a destination? Like what is the path it takes, and how is that path set up? This could be static or adaptive, and we'll see many, many different techniques over here. Buffering and flow control essentially asks the question, what do we store, or answers the question, what do we store within the routers and links? Do we store entire packets, parts of packets, etc.? And how do we throttle during oversubscription? For example, if you have contention and you have two things that are arriving at a link, and you have only capacity to send out one thing, one message, which one do you prefer? And how do you ensure that the other one also gets to its destination? There are many, many approaches over here also, as we will see. Okay, so this is tightly coupled with routing strategy, actually. These are not independent of each other completely. So topology affects the routing, and routing affects buffering and flow control. And topology also affects potentially some of the flow control methods you may be able to employ. Okay, so let me give you some more terminology. Unfortunately, I don't want to kill you with terminology, but it's good to know some of these things. Network interface, hopefully it's kind of obvious. This is a module that connects the endpoints or processors to network. So a network interface usually decouple computation and communication. Basically, if you want to send them, if a processor wants to send a message to the network, it goes through a module called network interface. We will deconstruct that in the next week's lecture. Maybe the network should be designed together with the processors, as we will see later. Link is a bundle of wires that carry a signal. Switch or router, essentially, this is something that connects a fixed number of input channels to a fixed number of output channels. Basically, you want to transmit a message from an input to an output. There's a switch that enables that. And we will see that you can use a switch to construct larger networks or multiple switches. And channel is a single logical connection between routers and switches. So these will all become clear, I think, if we start looking at topologies. But there's more terminology. Node is essentially a router or switch within a network. A message, which I've been kind of using, is the unit of transfer for networks, clients, processors, and memory. It could be a cache block, for example. For example, one cache sends a message to a processor with a cache block. A processor, it could be a request. It could be smaller than a cache block. It could be a message. It could be a coherence message, for example, like we discussed, right? It could be an invalidation message, like we discussed yesterday. So there are different message types also, as you can see. This enables communication. And then packet is different from message because it's really the unit of transfer for the network. So a message gets broken down into packets so that the network can transfer it on itself. And then packets gets broken down into flits. This is called a flow control digit. This is the unit of flow control within the network. How do you manage oversubscription, for example, or contention? Sometimes packets, a packet may be a single flit, or a packet may be multiple flits, as we will see. Hopefully that makes sense. I mean, if it doesn't make sense, I think you need to see the examples, as we will see later on. But essentially, message is a higher level abstraction. A processor sends a coherence message. That coherence message may be broken down into multiple packets, potentially. Usually, a single message like invalidation doesn't get broken down into multiple packets, but a processor, for example, sends a cache block to be written to some cache. And then that's 64 bytes. But your network may not be able to carry 64 bytes on the link, so that those 64 bytes get broken down into 8 bytes packets each, right? You have basically eight byte packets, and maybe each packet is broken down into a single byte because you want to do some sort of fine-grained flow control across the different portions of a packet. Okay, so there's some more terminology, direct and indirect networks. We will see examples of this. Here are the endpoints. Remember, endpoints are essentially nodes, you can think of it that way, sit inside or outside the network. So let's take a look at an example. Here, we have a bunch of endpoints over here. These may be processors, and a bunch of other endpoints over here. These may be memory banks, right? So in this case, you have an indirect network because these things over here, these are switches or routers. These routers are just doing routing. There's no processor here. There's no memory here. They're just doing routing. The sole purpose of this network is to do routing, and there's no endpoint associated with each of the switches. That's the idea. So you can see that there's more terminology. Radix of 2 means that you have 2 inputs and 2 outputs. And you may see this term. I'm going to avoid a lot of this terminology in the end, but abbreviation is radix array. So these routers are called 2 array, if you will. That means a radix of 2. These are fancy terminology that people have developed over decades. Yeah, I cannot fix it. But basically, you can have a radix of 4. We will see radix of 5 routers in a mesh. Okay, this is actually a butterfly network. You can this is a multi-stage logarithmic network, as we will see. It's a particular topology. This is a mesh topology. As you can see, this is a particular topology where endpoints are inside the network. So each endpoint has a processor or memory, and they're all inside the network, and also a router. Basically, each thing is a router, but also has a processor and memory over here. Okay, does that make sense? And why you may want to do something like this, basically, we will see that sometimes you want to connect processors to cache banks. In that case, this sort of network may make a lot of sense. But sometimes you want to individually connect each processor that already has a cache component or memory component, and you want to have a network connecting those. So basically, both of these are valid type of designs that you may have in a single system also. So within each node, for example, you may have one of these that connects the processors inside one of these over here to the caches inside that, right? So you can actually have networks within networks, as you can see. Okay, so I've already said this, I think. Mesh is direct in this case. In this particular mesh is direct because every node is both endpoint and switch. But this doesn't mean that all meshes are direct, right? You may actually have a node over here that doesn't have an endpoint, right? Okay, so now that we've got some terminology out of the way, let's talk about some more interesting things. So we're going to talk about topology, but even this topology has a lot of terminology. As I said, this is an area with lots of terminology. I'm going to give you a little bit more terminology, but then we're going to go into real topologies. So topology could be regular or irregular. Basically, you can have a regularity in the topology or completely irregular topology. Essentially, in the end, topology is a graph of nodes. It could have some regularity, or it may not have any regularity. We'll see a lot of regular topologies, rings or meshes, because it makes sense to actually do regular topologies. But some interconnects may not be very regular. Like if you think about the internet, for example, it doesn't have a really regular structure, right? Routing distance is going to be the number of links or hops along a route. Hopefully that makes sense. How many links do you go through along a route? Diameter is maximum routing distance within a network. This basically dictates the maximum latency within a network. And average distance is the average number of hops across all valid routes. We're going to talk about that a little bit. There's also something that you should be aware of, which is called bisection bandwidth. I'm not going to use it a lot, except for one case where we will talk about rings, for example. This is often used to describe network performance. Essentially, the way it's computed is you cut the network in half and sum the bandwidth of the links that you cut if you actually cut the network in half. Essentially, this is the minimum number of channels spanning 2 halves of the network times the bandwidth of each channel. It usually works for irregular networks. Irregular networks, it may be not so meaningful as this mentions. But this can be misleading because it doesn't account for many, many things. But you will see this in interconnect papers. And then there is a blocking versus non-blocking. I'm not even going to touch this one. So forget about this. But let's talk about topologies. Let's talk about interesting stuff, let's say. Any questions so far? I know this was a lot. Okay, So now we're going to see some of these examples of what we have used. So we're going to look at a lot of topologies in terms of connecting things. We talked about bus last time, but we're going to have a more formal treatment of it. This is really the simplest topology that you can build. And then we're going to talk about point-to-point connections. This is really the most costly connection you can build. And then we're going to try to get somewhere in between, let's say, get the benefits of point-to-point without the complexity of the point-to-point, for example. So crossbar will take us somewhere close there. But we'll see that crossbar is also not very complex and not scalable. And then we're going to talk about rings and trees and a bunch of different things, as you will see. So when we evaluate the topologies, we're going to look at cost in terms of the number of nodes, the number of routers that you have. And we're going to talk about latency, which is in hops, or it could be nanoseconds, but we're going to look at hops. And we're going to talk about potential contention issues. But there are many others that exist that you should think about, like energy, bandwidth, overall system performance. But as I said, these are not necessarily a function of the topology, right? These are, especially energy, is a big function of how you do the routing and flow control and buffering as well. So this is a bus, basically. It's a wire in the most fundamental form, and you have a bunch of units, nodes that are attached to that wire, right? And then there's some arbitration mechanism to decide who gets to send something on the wire. So for example, if node 0 wants to communicate with node 1, it sends a message on the bus saying that I want to communicate with node 1 and here's my message, right? Or it can do a broadcast, right? As we discussed yesterday, broadcast is easy because node 0 can say, everybody invalidate this cache block if you have it in your caches, right? So this physical medium that's shared between all of these nodes enables messages like broadcast easily. You can do a single message by sending the address of the node that you're addressing, or you can do a broadcast to all of them, or you can do a multicast. Basically, you can say this message that I'm sending on the bus should be received by node 2, node 4, and node 6. That's called a multicast, right? And bus enables this sort of communication very nicely and easily, as you can see, right? So it has its advantages. Okay, I already said this basically. And this is an example bus, right? It could be like this. You have processor. This is what we discussed yesterday. You have processors and caches, and then they communicate with each other through a shared bus. And that shared bus also enables communication with memory banks. So this requires some arbitration, which is not shown over here. So if two nodes request the bus, for example, 1 and 4 both want to send a message, there needs to be some arbitration on the bus, right? So that's important to think about. So the upside of bus, big upsides are really simple. It's cost effective for a small number of nodes. And as we discussed yesterday, it's very easy to implement coherence because it enables broadcast messages and it's a single point of serialization. That sounds good. Now, of course, this is not very scalable due to a large number of nodes. If you want to increase this number of nodes to, I guess, 64, 1024, what happens is you have electrical loading on the bus because you have a lot of things that are attached to the bus. And as a result, you get reduced frequency on the bus because there's some frequency of communication that's supported by the bus, and it may not be very large. Your latency is also increased because the distance increases, as we discussed earlier. And you also have limited bandwidth, basically. So you cannot communicate, for example, if you attach 1 million processors, for example, ignore even electrical loading and reduced frequency. If node 0 wants to communicate with node 5 and node 2 wants to communicate with node 4, they cannot communicate at the same time. Because they're sharing a single medium, right? And that's the problem with bus, basically. It has limited concurrency. It has limited concurrency in the end. So people have developed pipeline buses that essentially pipeline the buses that complicates the bus a little bit, but a lot of these fundamentals still remain, essentially. So you can actually have transactions on the bus, etc. A lot of these actually are implemented today, but scalability is still a problem. And as I mentioned earlier, if you have high contention, let's say if many nodes want to communicate at the same time, they all get serialized on the bus, right? You get basically fast saturation in the end. So serialization is a big problem, basically. Hopefully that makes sense. Any questions? So as I said, small scale multiprocessors implement buses, right? And once you go to 8 may be okay. But even 8 is pushing limits today, basically. Maybe 4 is better than 8. But once you start going to 16, 32, 64, people have avoided buses. So, okay, that's bus. So it's very limited in terms of its scalability. So here's another topology that's very limited in terms of its scalability, but it's on the completely opposite end. This is called point-to-point. Basically, every node is connected to every other. So 0, for example, is connected. It has dedicated links to every other node. 1 also has dedicated links that I want to appear, but apparently it's not appearing. Okay, 1 also has dedicated links. 2 also has dedicated links. 3, 4, 5. Basically, you keep adding dedicated links. So every node is connected to every other with a dedicated or direct or isolated links. And clearly, this looks nice. Whenever you want to send a message to another node, you have a dedicated link. That sounds good. It sounds terrible for broadcasting, though, right? I guess you could broadcast to everyone individually, but not everyone sees everything at the same time. So what if 2 nodes try to broadcast at the same time, right? Now you see the benefits of the bus, right? The bus serializes those broadcasts. Here, those broadcasts are completely independent, right? So it's very hard to coordinate in this topology. But before we go into a lot of those issues, clearly this is lowest contention because node 0 can transmit to node 7 while node 1 is transmitting to node 6, and they have nothing to do with each other, basically. Essentially, there is no shared medium between these 2 different pairs. As a result, there's no contention. So as a result of this, it can potentially have the lowest latency also. And if cost is not an issue, this is actually ideal from that perspective, right? But cost usually gets in the way, right? And other things also get in the way, like broadcasting potentially, if you want to do that. So this is highest cost because, as you can see, you have ON connections or ports per node. So node 7, for example, has needs to connect to everything else. And this grows linearly with the number of nodes you have in the system. And you have ON square links in the system, basically. Okay, maybe you don't care about cost, but how to lay out on a chip essentially becomes a huge problem with this. Maybe you can deal with 8, but once you go into 64 processors, imagine how many wires are going to be routed on top of each other. And how do you do that routing if you don't have enough metal layers? Let's say you have only 20 metal layers in your chip, you're basically out of luck. So that's not going to be doable in modern technologies. So that's one of the reasons why it's not scalable. So there are multiple reasons why it's not scalable. Certainly this ON square limits its scalability, but also the layout limits its scalability. And if you want to do coordination, it becomes harder to do coordination in this sort of topology that essentially doesn't share much across different node pairs, right? Okay, any questions? Yes. Can you press the button? Yeah, there needs to be some arbitration, just like in the bus. So here, for example, I didn't show the arbiter also. There needs to be some arbitration mechanism. So there needs to be some routing mechanism. If 7 wants to send a message to 2, for example, it needs to use the right link. So here, so you can think of that as a switch potentially that's combined, that's inside the node over here. But we're going to see the switches later on. Yeah, but you can think of that as a router. Yes, there's a switch basically that says node 7 wants to send a message to node 1. Which link do I use? And that also becomes a scalability problem because that's really ON, right? So if you have 1 million nodes that you want to communicate with, that's a switch 1 to 1 million switch basically. So contention is if two things want to, so as we looked at it on the bus, if 2 nodes want to communicate or send a message at the same time, do they conflict with each other in the medium? Here, there's very little contention, right? So if, for example, 7 wants to send a message to 6 and 0 wants to send a message to 5, they can go completely concurrently. There's no contention. Okay. Okay, so basically people try to get the benefits of this without the complexity of it. And that brings us to a crossbar. Here, crossbar is somewhat trying to achieve this, but without having point-to-point links. Basically, you have a shared link for a destination. So every node is connected to every other, but with a shared link for each destination. So it looks like this, basically. You can imagine, again, these are processors, these are memory banks, for example. And if 7 is sending a message to 0 and 6 is sending a message to 0, they share a link. But if 7 is sending a message to 0 and 6 is sending a message to 1, they can basically proceed concurrently. So you can see that contention increases in this case because there are some cases where there's contention on the shared link, but it's not bad in the sense that it's not a single bus, for example, right? Okay, so hopefully that's clear. So it enables concurrent transfers to non-conflicted destinations. This means that if the destination is different, you can have concurrent transfers, right? So, and this could be cost-effective for a small number of nodes. So there needs to be some way of basically arbitrating again, right? If 7 is sending a message to 0 and 6 is also sending a message to 0, every one of these can be sending a message to 0. So there needs to be some arbitration mechanism that serializes them. So you can think of this as kind of like a bus, and it is kind of like a bus actually. Okay. So basically, this is low latency and high throughput. That's the good part. It's also very regular. So compared to this is a lot easier to lay out, as you can see, right? You don't have any links that are going on top of each other. Well, maybe some things, but it's not that bad, right? So unfortunately, this is expensive. It's still expensive, basically. It's O n square cost. If you think about it, it's O n square. And again, the arbitration cost is still there, right? If you have 1 million nodes over here and 1 million nodes over here, you need to arbitrate between 1 million nodes to decide who gets to send a message to node 0. So because this kind of looks like a bus, the scalability is still limited. Hopefully that makes sense, right? It's good to think about it that way. So even though the goal was to actually achieve something like this, we fail kind of miserably, if you will, because the scalability is again limited. Okay, but as I said, this is used in small scale networks, just like buses. Especially core to cache bank networks in modern chips. These are some early examples, as I will show you in a little bit. So basically crossbar design, I don't want to go into a lot of designs of crossbars, but this could be buffered or bufferless. We're going to see more things like this later on. But for example, this shows the complexity of arbitration. This could be a bufferless crossbar, meaning whenever you send a message from 0 to 0, so processor 0 to processor, so memory 0 over here, you don't have any buffering for those messages. So you need to have some sort of arbitration that essentially says only one of them gets to use this link. So this is kind of like a bus again. But we'll take a look at it soon. So this is an example. Here they have buffers, as you can see. So essentially, this is an early Sun processor. You have cores, and you need to communicate with cache banks. You can see that there's a network that is essentially a crossbar. I mean, this doesn't exactly look like a crossbar over here, but if you analyze it, you will see that it's a crossbar, right? There's a shared link from all cores to one of the banks. And there's another one replicated for the other bank, and there's another one replicated for all of the banks, plus the non-cacheable unit, which is not shown over here because it's non-cacheable. Cache is over here. So essentially, it's a crossbar. And then the caches can also communicate back. Basically, there's the non-cacheable unit, sorry. So basically, caches can also communicate back, and the non-cacheable unit can also communicate back. It's another crossbar, basically. This is the link backwards, and there's a shared link to each core, as you can see. So this is a slightly different crossbar, and you can actually look at it from, I think it's a 9 to 8 crossbar. I believe so, yeah. So this is, you have 8 cores over here, and you have 9 units over here, including the non-cacheable. And you can see that there's some buffering they added because they don't want to build a bufferless crossbar where arbitration is complex. So you can see that each core can have 2 outstanding things, 2 deep queue. There's two different data transfer requests you can hold. And then there's some arbitration. You can see that the arbitration is a bunch of muxes over here, right? So there needs to be some arbitration mechanism over here. And they have a pipeline for arbitration, right? 4-stage pipeline. You get the request, and then request goes into the crossbar, and then you arbitrate, and then you get selected. If you're selected, you can transmit the data. So this crossbar takes some latency. So whatever looks nice, it may look nice like this, but the transfer from here to here actually takes 4 cycles. Well, 4 stages in this particular case. There may be additional interconnect latency that they don't talk about over here. So this is a real example, basically. Does that make sense? Okay. But in the end, it's a crossbar. And it occupies a lot of area, as you can see. This is an old chip, but you can see that core to cache crossbar, that's what they call CCX, occupies a lot of area in the middle of the chip. And I'm not sure if that's the whole area that they mentioned. Maybe there's additional area that exists that they didn't mark over here, right? Okay. So as I said, we will cover bufferless and buffered later on, especially next week. But crossbars can be built as bufferless and buffered. Bufferless means that essentially you need to have some sort of arbitration mechanism. You don't put things into a buffer. And whenever you different nodes may be injecting into this shared line, you need to ensure that only one of them gets to inject. So arbitration becomes a little bit more complex in the end. But usually people have built buffered crossbars, which makes things a little bit easier, although at the cost of buffers. Basically, whenever a node injects, it can just inject. And then the arbitration happens with the head of the queues that you have over here. So basically, there are 4 queues over here, and then there's some arbitration mechanism that decides which queue should get to transmit, right? It's a bit easier to do that sort of arbitration. And then there's some flow control mechanism that makes sure that this node doesn't overflow the buffers. So you will see that whenever you add buffers, you need to have a mechanism to ensure that you don't overflow the buffers. That's the idea. So in this case, it's simple because each node communicates to a single buffer depending on a destination. But we will see later on that there's buffering that's in more complicated networks, buffering actually leads to some other issues in the entire network. So here, each node, so this node wants to send a message to this whatever, it could be a cache bank. It just needs to communicate with this buffer, right? Okay. So basically, buffered crossbars enable simpler arbitration because you just need to look at the head of the queues over here, and you don't need to arbitrate across the links over here. There's some more detail over there that I'm skipping. It enables efficient support for variable size packets. So if you have actually variable size packets, you can buffer pieces of them inside these buffers. But unfortunately, it requires now more complexity, right? You have n square buffers. And if each buffer is, let's say, m deep, you have m times n square complexity, right? So this is going to be a fundamental trade-off, as we will examine it later as well. Do you build a network without buffers, or do you build a network with buffers? And this is going to be interesting. In the end, I think the best option is going to be somewhere in between, as we will see. But it depends, I should say. It depends on the traffic that you're observing, and also the complexity that you can tolerate in the network. Okay, so crossbar, as I said, it's not scalable, and also it's costly. The question is, now can we get lower cost than a crossbar while still having low contention than a bus? That's our goal. And people have proposed lots of topologies to this end. One of the ideas is multi-stage networks. So let's talk about those. How many people have taken a networking class here? Okay, have you covered some of these topologies? Maybe not, or you don't remember. You have covered multi-stage networks, for example. Okay, yeah, I think this is a very different approach compared to networking. Networking classes usually tend to be higher level, if you will. They talk about higher level of abstraction. But here, even though it's a very similar concept over here, we talk a lot about topology in computer architecture because you really need to connect the nodes to begin with. And this is actually influenced a lot by supercomputer design in the past. Okay, so multi-stage networks, they look like this basically in general. And the idea is they're indirect networks, meaning there are a bunch of switches that are not endpoints. And they exist, and there are multiple layers of them that exist, and they connect the nodes, endpoints, if you will. So this is an example of Omega network. It looked like this. You can see that there are 2x2 routers, 2 input, 2 output, or 2 array, or routers of radix of 2, if you will. I'm throwing back the terminology that I mentioned earlier. And the idea is, so this could be, again, the cores and the cache banks, right? But instead of a crossbar, now we have something a lot simpler, if you will. Well, it looks simple also, right? It consists of 2x2 routers, as opposed to, if you think about it, as opposed to, I don't know, here you have n to 1 router over here, right? You can think of it that way, right? So these are much simpler routers in the end. So arbitration is very simple in each of these over here. But now, in order to be able to make the network work, you need to have a logarithmic number of stages. Now, what does logarithmic mean? It's logarithmic in the number of router radix. So it's really log 2 of n over here. If your router was a 4x4 router, then it would be logarithmic of logarithm 4 n, basically. So it depends on the router design. But 2x2, it happens to be the cheapest and the least complicated type of router. So people usually design these with 2x2 routers. But of course, the latency increases. So basically, if you look at this network, now you can communicate still from any node to any other node, right? You can ensure that by looking at it. And the cost of this is n log n. If you look at the number of routers, basically you have, I mean, in the big O notation, of course, right? Basically, you have a log n number of stages. This is 8. Log 2 to the 8 is 3 stages in this particular case. And then you have n over here on this dimension, order n, clearly. If you want to be exact, it's really the number of processors divided by 2, right? Which is still order n. So basically, the cost is n log n, order of n log n. Latency is really how many hops do you go through. It's log n in this particular case, right? To go from one node over here to a destination, one source over here to a destination over here, you need to go through log n number of routers. And it's constant, basically. Everybody goes through log n number of routers, right? So there are many, many variations of it. I'll show you some variations. You don't need to know the exact details of the variations. It basically, the variations differ in terms of how these switches are connected to each other. And as a result, you have different contention patterns. Okay, does this make sense? Okay, now we're getting somewhere that's much less complicated, as you can see, right? This I can build a lot more easily. I just built a 2x2 router switch and connect them like this, right? And hopefully I have enough wiring resources to enable things like this, right? Now with 8, it doesn't look that bad. If you go to 64, okay, maybe you'll start scratching your head. So wiring always becomes complicated. So this is actually essentially the issue with supercomputers, for example. If you look at a supercomputer, if you see how things are connected, a nightmare is how you actually wire these processors. And if you've ever seen a picture, I should really have added a picture of a supercomputer. If you've ever seen a pigure of a supercomputer, you have lots of wires and lots of cables. And if you don't connect some things correctly, you may actually get completely useless things, and you may need to figure out how to fix it. So basically, that's the problem with a supercomputer. As this increases and as this increases, your wires become a mess. Even though you may be able to connect because you have huge wires, clearly you have space, right? Hopefully you will be able to connect. You need to figure out what to connect where, right? Okay. But on chip, you're actually much more limited potentially in that particular case, because if you have 100 nodes over here, even something like this, you're going to have some overlaps in terms of wiring. So how are you going to route the wires so that they don't overlap with each other, such that they don't exist the wiring resources that you have, they don't exhaust the wiring resources that you have, will be a problem. But still, this is better than a crossbar in the end, in terms of scalability. Okay, any questions? Yes. Yeah, don't worry about that. These are different variations. As you will see some examples soon. So this basically, as I said, it depends on how these switches are connected. That's right. Yes, that's the goal basically. So let's take a look at the contention over here. So this is we're going to look at two things that are trying to access a particular cache bank, let's say, destination 111. Let's assume that processor 111 is trying to access this cache bank. So it needs to go through this route, right? So there's exactly one route it can take. So this switch, you need to go through, basically, this switch needs to route the message from here to here, and this switch needs to route the message from here to here, and this switch needs to route the message from here to here. Whereas if another node is also trying to connect to 110 in this particular case, it has to go through this, right? This switch needs to route the top input to the bottom output. And then this switch needs to route the top output, top input, its top input to the bottom output. Now, if these two messages arrive at the same time to this switch, you have a contention, right? And this is why this is a higher contention compared to a crossbar, right? In a crossbar, this green path and red path does not cross because there are two different destinations. Here, unfortunately, because we're frugal in terms of what we implement, there's contention, right? So this is why these multi-stage networks make a trade-off in terms of cost versus contention. So you have a conflict or contention in this router. And depending on the access pattern, this could actually be very serious, as we will see in a little bit. Okay. So essentially, what I just showed you is multi-stage network restricts concurrent transaction and receiver pairs compared to a crossbar, basically. Basically, crossbar, if you look at over here, look at this picture. Well, this picture is also okay. Concurrency is much higher in a crossbar. If the destinations are different, you basically can send messages to those destinations without any problem. But here, you have restrictions. Okay, but it's much less costly than a crossbar. As we said, all n log n for many networks, actually, it's all n log n. But if you look at the switch itself, it's actually a 2x2 crossbar. Right? This is good to realize as well. So this switch, each of these switches, if we go into a little bit more detail, it's really a 2x2 crossbar. It has 2 inputs, 2 outputs, and you have a 2x2 crossbar, right? So the destination is shared. And that's the reason you're having contention over here. The destination, well, in that particular case, the destination, output destination was shared and 2 inputs were arriving at the same time. So clearly you cannot transmit 2 things at the same time. So one of them needs to wait, right? So each of these is a 2x2 crossbar. So that's how we actually built this network. But the network is not a crossbar in the end. Okay. So there's one thing that I will discuss, which is circuit switching and packet switching, because this is a very fundamental high-level decision that you need to make. The way this looks says nothing about how you actually route the signals, right? For example, if you want to send a message from 0 to 7, one way of doing it is through circuit switching. Basically, the idea over here is you somehow set up the crossbars over here, the routers, along the path, and you completely set it up to transmit data before the data is transmitted. Essentially, you can think of it as pre-configuring the switches. What does that mean? Basically, if you want to send a message from, actually, let's take an easy case. From this 7 to this 7, what do you need to do? First, you need to actually send a control message saying, I want to send messages from 7 to 7. So let's set up the routers. So this router will be set up such that this port will be connected to this port. And this router will be set up such that this port will be connected to this port. And this router will be set up such that this port will be connected to this port. You can think of it as programming. It could be actually reconfigurable. But basically, and then you send a message, and this routing is done such that you send the message and the message just flows through this as if it's a single wire. Of course, there might be buffering that happens in between, but it's like a single wire. No routing happens while the message is sent. Routing kind of happened before the switches were pre-configured. So that's the idea of circuit switching. You pre-configure the switches, and when you send the message, there is no special routing that happens. You did the routing earlier, statically, if you will. So this way, you can, for example, configure these switches to operate such that they go from 7 to 7. Nice. And then you can configure these switches such that they go from 5 to 5. But those switches cannot be used for anything else, right? That's the downside of circuit switching, basically, because you pre-configure the switches such that they only do one thing until you go back and reconfigure them. Right? So that's the downside of it. The upside is there's no need for buffering since switching is static once the path is set up. The upside is, the downside is basically you cannot, concurrency is limited right now. For example, if 7 is set up to send message 7, 6 cannot send essentially any messages, right? Because it has to go through this switch, and clearly 6 is not wired. This switch is not configured to send any message from this switch at that point, right? So you can see the downside of circuit switching and upside of circuit switching in this picture. But if you can actually ensure that circuit switching, if circuit switching is useful, it could be very, very efficient. You can see that, right? There needs to be no buffering. Packet switching, on the other hand, usually requires buffering. That's a packet-based system. And the idea is basically packets hop from router to router, pending availability of the next required switch and buffer. And you dynamically determine the route. There's no static setup. A packet arrives over here, and then you decide which one to send to which output port. Okay? So if 2 packets may arrive at the same time, 6 and 7, And then the switch has a prioritization mechanism that says, okay, I'm going to pick 6. Well, okay, maybe 6 wants to go this way and 7 wants to go this way, depending on the destination address, of course. Then they can both be sent on different output links, right? So you have a lot more concurrency right now. If you do packet switching, 6 can use the switch to go this way, and 7 can use the switch to go this way, right? So actually, I was a bit wrong when I said 6 cannot send anything over here, right? 6 cannot send anything this way. Once 7 is set up this way, 6 cannot send anything this way. But 6 can potentially, this switch can be set up to send something from 6 to this output port, while 7 is also sending something from this output port. So basically, there's some concurrency. So go back and correct that. But 6 cannot send a message this way, because this port is being configured so that 7 can, the lower output port is connected to the lower input port is connected to the lower output port. Okay, but here there's no restriction basically. Dynamically, every cycle, every decision cycle, let's say, this higher output port can be connected to either the higher output port or lower output port, and this lower input port can be connected to the higher output port and lower input port, depending on the contention, essentially. Okay, hopefully that makes sense. Okay, so let's take a look at the trade-offs over here. As I said, circuit switching sets up full path before transmission. It's static routing. It's a method of static routing. Packet switching performs routing per packet dynamically in each router. Okay, I've already said this. So the downside is no one else can use those links while the circuit is set. So they can use the router. So basically the key is the links are configured, but as long as you're not using the same link, you can use the same router essentially, because the router is supposed to be able to transmit data to different outputs concurrently. So whereas packet switching, you route each packet individually, possibly via different paths. If the link is free, any packet can use it. So upside of circuit switching is faster arbitration, because dynamically you don't make a decision, statically you set up the circuit. There's no arbitration that you need to do essentially dynamically. No buffering, so you don't need any buffering in this particular case. But downside is setting up and bringing down the path takes time. You need to have some control messages to set up the routers essentially. Those are special messages that you need to send. And as I said, path cannot be used by multiple flows concurrently. This is each link that you set up cannot be used. Packet switching is potentially slower because you must dynamically decide which packet gets which output port. And it needs some way of handling contention, for example, via buffering. But we will see other contention handling methods later on without buffering also. The big upside is there's no setup or bring down time. And an even bigger upside is it's more flexible. Essentially, it doesn't underutilize the links. Every link can be utilized in the system, assuming that it's possible to do that with the access pattern that you observe. Right? Okay, so I wanted to cover switching because it's really important, but it's a high-level choice. It's a choice that's independent of topology. It's a high-level protocol on how a message gets sent to a destination. It affects routing, especially how you do the routing and how you do the router design. But it's not dependent on the topology. Some topologies may be more amenable to circuit versus packet switching in terms of the path, in the sense that because circuit switching really limits concurrency, some topologies that are very high path diversity, meaning very high potential concurrent paths, are more amenable to circuit switching. But if you don't have a lot of paths that many different things can go through, you may not want to do circuit switching in that case, because you're underutilizing your already restricted number of paths. Okay, any questions? So these are actually implemented in real systems. Feel free to ask questions, but this is a system that was designed. These are Tylera. It's basically one of the first very simple many core systems. These guys had 64 processors initially, and then 100 and more than 100 processors also. These are very simple processors, and they use a topology that we will see later, two-dimensional mesh. It looks like this basically. And they had actually 5 networks, 5 different types of networks we will see later on. So we're going to see what these mean later on. But 4 of them were packet switched because they needed that sort of dynamic fine-grained switching. Like these are some examples. Usually they're cache networks and I/O packets, core-to-core message networks. But one of them was very circuit switched. And the reason was here, basically, they wanted to enable communication from one node to another node where one node actually streams lots of data. So if you want to, for example, communicate between a processor to, I don't know, a GPU, in this case, they didn't have a GPU, but another processor, let's say, and you want to communicate 1 gigabyte of data, you would set up the path and you would send all the data packet by packet, and there's no need for dynamic switching, right? If it's circuit switched, you set up the path and you just exclusively utilize that path. That enables low latency across the network for a large amount of data. So if you're doing video streaming from one location to another, for example, this could be very useful. But if you don't have, let's say, if you don't have a huge amount of data to transfer that goes from one source to another destination, packet switching may be a potentially better idea. Because the reason this is useful for huge amounts of data is because you're sending lots of packets, so the connection setup and tear down time is small compared to the amount of data transfer time. And also, you don't need to do switching, dynamic switching for every single packet, so your latencies are low. Okay, any questions? Okay, so these are examples. As I said, there are many multi-stage networks. This is actually an earlier example than what I showed you earlier. Omega network was, this is a Delta network. I don't expect to remember. I myself don't remember exactly how these things are different. But basically, the switches are wired in different ways. That's how they're different. In this case, each stage has different routers. And again, this is actually the original paper that motivated multi-stage networks. This is another multi-stage network that we've seen. That was the Omega network. This was used in an NYU Ultra computer. Here, all stages are essentially the same. It's good to think about that. That may make it a little bit easier. I will mention one thing about this network, because this is actually interesting, because this network was able to do limited computation. So we talked about these switches as not having computation capability. They're not endpoints, right? But these folks decided to add simple operations to be performed in the network. You can think of this as an early example of computation inside the network, right? Inside the switches, which a lot of people are looking at in the networking community these days. Can we do computation inside the routers, for example? It's kind of like computation in memory, but a router today is a very complicated system, right? So it's a bit easier than computation in memory, I would argue. But basically, this idea goes back to at least this work, where they basically, their idea was to combine multiple operations on a shared memory location. And they had a very specific purpose in this case. Basically, for example, you can see that they're doing test and set on a variable. Why? Because they're building multiprocessors. This is a supercomputer. And their goal was to do fast synchronization across the computer. So if a lot of the computers wanted to get a lock, for example, or test a synchronization variable, you could actually do that testing and setting inside the network while the data is coming back to the processors, such that they can synchronize in the network, essentially. That's the idea. So the general operation is really the fetch and add operation. Test and set is a one specific example where you're not doing an add, but you're setting a variable. And it looks like this, basically. Each switch is capable of doing fetch and add. And there's a memory location, and there's an increment that you can add. Basically, the switch returns M and replaces M with M plus I. Now, this is a clever thing, because this is nice when all of the processors are trying to modify a shared variable, for example. They're all trying to obtain a chunk of the array, for example, right? They all want to get which part of the array they want to operate on. And there's a single beginning address. And each of them is incrementing the array index that the other one is supposed to see by I, let's say. It could be actually a variable depending on which processor is sending the message, because it's based on messages, as you can see over here. So basically, everyone can actually see the value of the memory location in the network without going through ping-ponging that we discussed yesterday, right? Okay, so I gave you the high-level idea how it works. You got to read the paper. So there's some implementation issues that you need to make sure it works. Does that make sense? Okay. So this sort of combining operation actually reduces synchronization latency, and you can imagine why. And they actually report in this paper, let me go back. Yeah, in this paper, the benefits of this sort of operation. Okay, so this is another example. Again, I don't expect you to remember the networks, but butterfly is actually easy to remember. It has a particular type of connections, as you can see. Kind of looks like a butterfly. But basically, it's indirect, and it's used in real systems, I guess fancy real systems that didn't succeed, let's say. But basically, conflicts, you get a lot of conflicts depending on the access patterns. And if you try to randomize the route selection, that helps. We'll talk about that later on. Okay, we covered a lot of topologies. Let's take a look at some examples. This is crossbar. Remember, this was costly. This is multi-stage logarithmic, and we're going to get to a mesh soon. Again, I don't expect you to remember blocking or non-blocking, but basically, the downside of multi-stage logarithmic is it's still O n log n. So the question we're going to ask is, can we get lower cost? And mesh is going to take us to a lower cost, and it will also have additional benefits. But unfortunately, it will come at the expense of some latency, as we will see. Okay, so before we get to mesh, I want to cover something much simpler, basically, because I think you can think of mesh as a way of connecting what I'm going to cover next. But keep this in mind. Every network can be added, and you can analyze it this way. So let's pull back a little bit and try to decide, okay, we have a bus. Bus is not what we want, clearly. It's not scalable. What is the minimum thing that I can do to improve the bus, as opposed to coming from the direction of what is the thing that I can do so that I can get the crossbar crossbar characteristics as much as possible, right, at a lower cost. That's what we did, basically, going from crossbar to multi-stage logarithmic. We asked the question, what can we do to get the benefits concurrency of a crossbar as much as possible without the cost? And we kind of achieved that, right? Of course, at the expense of latency, clearly. So if we ask the question, going from bus to what is the simplest thing that I can do to improve the concurrency while adding as little cost as possible, that brings us to a ring, essentially. And ring looks like this. Again, this is processor, memory, and switch, if you will. So there's still a router over here, as you can see, switch. But basically, it looks like this. Every node is connected to the next node, and the next node is connected to the next node, and then eventually they get all connected through a ring like this. Okay, I already said this. Each node is connected to exactly two other nodes. Nodes form a continuous pathway such that packets can reach any node. So this is cheap. You can see that it's O(n) cost compared to O(n) log n in the multi-stage logarithmic, and compared to O(n) square in crossbars, right? So that sounds good. This is high. Downside, of course, downsides exist. This is high latency, O(n). And kind of similar to a bus, it's not easy to scale, but it's not much better than a bus. So why is it much better than a bus? Because if you look at these links, now you've partitioned them, right? Links are partitioned between nodes. There's no shared link across any node. So in that sense, it's much, much more scalable than a bus. So that's the good part. But maybe it's not hugely scalable, because as you increase the number of processors, your latency increases significantly, right? In that sense, it's similar to a bus, but you can still build it. Your latency may be high, but it's much easier to build. So basically, bisection bandwidth remains constant. I wanted to add it over here, because if you sever the links over here, so as you keep adding nodes, to a ring, what happens is you basically keep extending the ring. Bisection bandwidth remains constant. Remember, bisection bandwidth, you cut the network at a point where where a maximum number of links cross. And that remains constant, basically. Regardless of wherever you cut the network, you have two wires, essentially, if you think about it. You want one wire over here and one wire over here. And that doesn't change at all, regardless of how many nodes you add. That's true for the bus also, by the way. That's not true for a crossbar, if you think about the crossbar. You keep adding links as you keep adding nodes in a crossbar, so the bisection bandwidth actually increases. So that's why these networks are a bit more scalable. Okay, but these are used because these are simple, as you can see, right? Simple and more scalable than a bus. A lot of modern multi-core systems actually use these networks. So that's good. In fact, Intel Larrabee, which kind of died, I guess, which was Intel's competitor to NVIDIA GPUs. They wanted to design x86 processors to compete with NVIDIA GPUs, but they did not succeed, even though they were very ambitious. They had a nice bufferless ring, which they talk about in their papers. They didn't die because of the ring, though. They died because of the software complexity, essentially. It was very difficult to do, for example, shader calculations in something that's not specialized like a GPU. They wanted to have general purpose, and they had a lot of SIMD units, yes, but they still couldn't get the software to be as efficient as it would be on a GPU. Okay, that's a side thing. So basically, rings are actually multiple types of rings. What I showed you earlier was kind of agnostic. But it could be a unidirectional ring. Unidirectional ring means that there's only one direction. As you can see, you go from left to right. There's no right to left ring. So basically, if you look at each router over here, it's a 2x2 router again. 2x2 crossbars are actually very useful. Rings are also used to built based on 2x2 crossbars. Why is it 2x2? Because this node can inject something, and that can go here, and this input that's coming from the actual ring can go either to this node or can keep traversing the ring, right? That's the idea. So basically, you have a single directional pathway in a unidirectional ring. It's very simple. So you get very simple topology and implementation. This is very, very easy to lay out, as you can see, right? You keep stamping a bunch of nodes, right? And the distances are very short, as you can see. And again, this distance may look long, but when you lay this out, you don't do it this way clearly, right? What you do is you kind of like have a box like this, and then the ring goes like this, right? It's not, you clearly don't build a wire like this. This is just pictorial. Yes? Yeah, that's true. That's true. Basically, you will send a lot of messages, and buffers can be full. Yeah. I mean, that's true, but that's true for a lot of the topologies. Yeah. Yeah. If you send large messages, eventually there will be networks that will be saturated. Yes, we will see, and we will see that basically. So I think what you're getting at is the saturation throughput of this sort of topology can be very low because there's not much connectivity. As a result, you saturate very early. Okay, I think we've kind of so this actually gets you reasonable performance if the number of nodes is low and the performance needs are not very high. And again, here you get n/2 average hops, latency assuming that everybody communicates with each other at random equal probability, and latency depends on the utilization. Okay, but usually single directional rings are less costly, but they have a downside in the sense that you don't go both ways, right? So for example, if this node wants to communicate with the immediate left node, you cannot do it immediately, even though you have a single hop conceptually, because that link doesn't exist. You have to go through all of the other nodes, basically. That's why people have developed bidirectional rings. These essentially provide multi-directional pathways or multiple rings. You can think of it as multiple rings, essentially. Multiple rings. One ring goes from left to right, the other ring goes from right to left. And this reduces latency and improves scalability. But now you have a slightly more complex injection policy. You need to select which ring to inject the packet into. So basically, if you have two rings, one is going from left to right and the other is going from right to left, you have to decide whether a packet that you want, you can use both of them to send messages to any processor, clearly. But now you have to decide which ring to inject into, right? And this depends on the distance between the source and the destination. This depends on the contention on the network. And you may not actually have make the best choice if you actually look locally only. Does that make sense? Okay. Okay, so a lot of existing systems use some sort of bidirectional ring. This is, what is it, Intel Alder Lake, for example. And you can see that these actually occupy a lot of space also. Even though these are supposed to be simple, they actually occupy a lot of space. Okay, so rings are not actually, their scalability is limited, as I said. And maybe people can connect 32, 64 processors, but once you go beyond 64, it becomes difficult to scale these things because of the long latencies, as we discussed. So people have looked at hierarchical rings. These are some examples. So what does a hierarchical ring means? This is a level 1 ring, if you will, that connects 4 processors. It could be a bus also. And then there's a level 2 ring that looks like this, right? So if you want to send a message from here to locally, you just stay on the local ring. But if you want to send a message from here to some other quadrant, in this particular case, the message needs to hop on to the global ring and then hop off from the global ring to the other local ring. So this is one way of doing it. There's another way of connecting it. There are more bridge routers. These are called bridge routers. And you can see that there are 4 bridge routers over here. But here, there are 2 places in each local ring where you hop on or hop off from the global ring, basically. And clearly, bridge routers add more complexity, right? Here, you can see that there are 2 global rings, and now there are 4 bridge routers that enable connectivity between the local and global rings. And then here, there's a larger hierarchy over here. And again, this is just to show that these are hierarchical rings, but in some cases, some of the communication may be over buses. So here at the local level, you may have buses, and then you may connect to the rings. So it can actually mix and match topologies as well. So the big benefit of this is clearly more scalable than a ring, and it's lower latency also. If you have a single link, your latency is determined by ON. Here, your latency is really determined by the local latency to reach a bridge router, and this latency over here, and then the local latency over here. So it could be actually very, very fast, depending on how you design the global ring, right? So it's good to think about it that way. There's a lot of design choices that you can have. And also it's very regular, as you can see, right? The layout of this is quite regular. So I'm a very big fan of hierarchical ring topologies in general. Okay. Any questions here? I'm not going to go into a lot of detail, but clearly as you add more routers, complexity of decision-making increases here. Okay, if you're interested in it, we've done a lot of work on this topic, and you can take a look at some of the papers. And this actually describes the design implementation of a mostly bufferless hierarchical ring. So in fact, as I said, Intel Larrabee had a bufferless ring, but basically in these local rings, you don't need any buffers. Ideally, you can get rid of a lot of the buffers over here because you can keep the ring small, and also you can increase the frequency significantly by reducing the buffers. When the place where you really need buffers is usually, I mean, even there you don't need buffers actually, but when you're connecting from a local ring to a global ring and vice versa, you need some buffering over there because if you don't have buffers, then you keep traversing in this link until this link becomes available. We're going to talk about bufferless flow control, but basically a mixture of buffers and buffered and bufferless rings can actually get you to a nice space. Okay, so there's more that you can read about. And this actually we implemented in some real systems, a version of what is described in this paper, very similarly, even though it's very cryptically described, is implemented in these processors that were introduced by Huawei recently. And they talk about the benefits of these rings. So they have this multi-ring architecture, and some of the contention control mechanisms are actually described here. Okay, any questions? Yes. Like circuit switching versus packet switching, okay. Mm-hmm. Basically, each different packet needs to be routed dynamically, right? You know the route potentially, but okay, are you asking about the what is dynamic about the switching? Mm-hmm. Well, in that particular case, maybe, but in some cases, route may not be also known, right? Mm-hmm. Yeah, in that case, it's known, right? This one. I think you're going back to these slides. Yeah. So basically, what's dynamic about it is, root. Once you know that 6 is going to communicate between 7, yes, that's known, right? But the question is basically whether you set up the path such that the switch is configured that way, right? So you can set up the path statically such that this switch always transmits the top input to the bottom one, right? And then this switch always transmits the bottom one to the bottom one over here, right? Now, this does not enable you to transmit from here to here. So dynamically, you may need it, right? Dynamically, there might be a message going from 7 to, I don't know, 4. And then you cannot use it, right? Mm-hmm. Exactly. Is it whether it's dynamic or static? Yes. Okay. Okay. So let's talk more about topology. So these are rings, and I think there's a lot of interesting things to be done here. A lot of people actually looked at meshes when multi-core systems are being designed, actually. So if you look at meshes, they also have very regular topology. And now we're getting somewhere between these point-to-point and I don't know, buses without having the complexity of the crossbar. So these topologies are actually quite interesting, especially when you analyze them also. But basically here, each node is connected to 4 neighbors, except for the edge nodes over here that you can see. But in the middle nodes, you're connected to 4 neighbors, north, east, south, west. And cost is ON in this particular case, as you can see also, order of N. Average latency is square root of N. You can do those calculations. And you can see that this is very easy to lay out on chip because very similar to what we have seen in rings, the links are only between neighboring nodes. There's no global links. You only have links between neighboring nodes, and that enables laying out easily. Clearly, there are no links that go on top of each other here, right? So it's regular and equal length links. Now, this enables path diversity also. There are many ways to get from one node to another. I mean, that's true for something like this also. That's not true for crossbar. Crossbar is very limited. That's not true for point-to-point. But here, you can see that there are many ways from getting from one node to another over here. You can actually traverse many different ways, right? And the ways actually increases with the complexity of the network. So that's true for mesh also. If you want to go from this node to this node, you can basically take lots of potential paths. So again, static switching using only one sets up only one path and uses that. But dynamic switching, each packet that gets communicated from this node to another can go from any possible path over here, right? So that enables actually reduced contention. That's very useful if you have a lot of load on the network. So the saturation throughput of a network like this is actually much higher than the ring that we have seen earlier. So this is used in the Tyler networks that we discussed, and there are many other on-chip network prototypes. Okay, so one problem with mesh is that these edge nodes. So these edge nodes actually, unfortunately, have low connectivity. As a result, they cause some headaches. And what are those headaches? Basically, applications or things that are placed over here get penalized a little bit. And performance becomes very sensitive to the placement of the task. If your task gets placed on the edge versus in the middle, you get very different performance in the end. So Torus avoids this problem. Basically, the problem with mesh is each node is not equal. Different nodes are heterogeneous in terms of their connectivity, right? This node, edge nodes are actually the worst because they're connected to only 2 neighbors because there are no other neighbors over here. So Torus avoids this problem by basically adding links across those nodes so that everybody gets connected to 4, let's say, neighbors, 4 other nodes. So it looks like this. Now it looks a bit interesting, right? So you have a ring that's like this. You have another ring that's like this. And everybody's connected to 2 rings. Well, yeah, 2 rings. So you can think of Torus as rings of rings, but that's not exactly like that because it's really a 4x4 router that you have over here. But you can make it like a ring of rings if you can switch between one ring to another ring also, right? So basically what I'm describing is another topology for you, but it's not exactly a ring of rings in this particular case. So this enables higher path diversity and also bisection bandwidth than mesh. If you actually cut the network, you have more links compared to mesh because there's one more link that we added over here, one more link, one more link, one more link. So I actually have a lot more links than a mesh and also more paths. But of course, this is higher cost than a mesh. It's a bit harder to lay out on chip because now you're unequal link lengths. And it's a bit harder to do it. But it's not impossible. Basically, you can weave the nodes to make internode latencies kind of constant. And this is one way of doing it, as you can see in this picture. But it's not as simple as a mesh, basically. Okay. I mean, we can go on and on topologies. I don't want to spend a whole lot of time, but people have also talked about trees. We've seen this in the clock distribution network, but this could be a multiprocessor network also. Basically, this is an example tree. This could be direct or indirect, depending on. So these could be the processors, and these nodes could be actually just communication nodes, just switches basically, or all of them can be processors basically, and they also switches, of course, right? So this is another planar and hierarchical topology. And again, this is very regular. And you can see that it has similar characteristics to mesh and rings. The links are just between nodes. They're local links, right? There's no global link over here. I mean, you can think of this as a global link, but it's not global, right? It's just between two nodes in the end. But it connects, of course, two branches of the tree. This is called a fat tree because as you go up higher in the hierarchy, the bandwidth between the links also increases, with the expectation that the communication over here is less than the communication over here, which is less than the communication over here, right? Yeah, depends on the access pattern, of course, right? So this is good for local traffic. For example, if you're adding numbers over here and then propagating it to over here, that sounds good, right? You can actually enable that sort of traffic. You can basically have a huge amount of addition or histogram computation. So whenever you're reducing, this is actually very good for reduction in general. These are also called reduction networks. You may have heard of that. But basically, this node is doing some computation, and then it's merging its results with this node's computation. That merge happens over here, or that reduction happens over here. That's true for these two nodes. That's true for these two nodes. That's true for these two nodes. And then they basically pass on their values over here. Another reduction happens over here. Another reduction happens over here. And then maybe there's another node over here that's not shown in this particular case, but it's possible to do that. Or one of them communicates a message to the other. And then if it finishes the reduction. So whenever you're doing reduction operations like this sort of tree is very useful. And it's cheap also, well, relatively again, ON cost. And it's very easy to lay out, as you can see. And these are implemented. One of the downsides is the root. In this case, there are kind of two roots. But here there's one root. Can become a bottleneck if the communication pattern is such that there's a lot of communication at the top. But if you have fat trees where the bandwidth increases as you go up the levels of the tree, then you can avoid that problem. And this was introduced again in multiprocessors. This is an example from an old times. This is actually very interesting multiprocessor connection machine, the 5th version, if you will. You can see that there's a fat tree based on 4x2 switches. It looks like this basically. You have 4 inputs and then 2 outputs over here. And then there are a bunch of top nodes over here. And these connections are fat in the sense that their bandwidth is much higher than this lower level. And they basically employ some routing mechanisms. We're going to talk about routing over here. They randomize the routing so that they minimize the contention over here. And they actually have a lot of operation support in this tree, like combining, like we discussed earlier, because that enables fast synchronization, multicast, reduction. They actually support some reduction operations in the network. So it's actually a very, very interesting design. Again, I won't talk about all of these, but you can read some interesting papers. And this is from one of their papers, as you can see over here. Let me see. Yeah, I don't think I have anything else to say because I already said everything I said that's written over there. But okay, well, one of the things that I should probably say is that as more processing nodes are added, the number of levels of the tree increases, allowing the total bandwidth across the network to increase proportionally to the number of processors. So this is a scalable network. Okay, so we're getting to the end of the topology, and we're going to introduce a bit more complicated topology right now, which is hypercube, which has interesting characteristics, not all of which we will go into. But this was actually designed for message passing computers. So these are n-dimensional cubes, basically. So this is 0D, 1D, 2D. 3D is the cube that you're familiar with, probably. That's our regular cube. But there's a 4-dimensional version of it. And there's a I believe this is 6-dimensional version, but don't quote me on it. Well, maybe 5-dimensional. How many do you see over there, 32 or 64? I cannot tell. We'll see the 6-dimensional version soon. But if you look at this, it has very nice characteristics, actually. Latency is on the order of log n. Radix of the router is order of log n. And the number of links is O n log n. And this was, so it's low latency. It's a very low latency network. Unfortunately, it's very, very hard to lay out and design. Once you go into 60, okay, maybe 60 is okay, as we will see in the next slide. 7-dimensional, 8-dimensional, and these are small numbers. 8-dimensional means 2 to the 8, 256. What if you want 20-dimensional, right? 2 to the 20, which is what you perhaps want in a supercomputer at least, right? So it becomes very difficult, basically. So it's not a very scalable topology, but it's a very interesting idea in the end. It was used in this Cosmic Cube, which was a 64-node message passing machine, which was one of the first big message passing machines, if you will. And this is, I think, the 64-node, 6-dimensional hypercube. And I didn't check the correctness of it, but it may be, assuming it's correct, it still looks like a mess, right? So you can see that this is hard to lay out. But this is a much smaller hypercube. This is a 3-dimensional hypercube. You can see there are only 8 over here. Okay, and they say that this is a 2-dimensional projection of a 6-dimensional hypercube. Clearly, this is not. You're not going to have. Well, if you're actually building this on chip, it's kind of like a 2-dimensional projection, right? You need to think of it that way because you need to do the assign your metal layers based on that 2-dimensional projection in the end. Okay, so I'll leave you with that. But this is a picture that I borrowed from this paper, basically. These folks suggested that this sort of configuration is not very good. While a lot of people were building this sort of configurations where we had processors and storage, the Caltech Cosmic Cube paper suggested that you should really be building this sort of connections because this leads to lower latency. So this is a paper that argues for lower latencies in the 1980s, as you can see. And I think this is a very forward-looking and nice paper that talks about message passing also. If you look at this, the latencies over here are relatively high, and they argue that the latencies over here are relatively low. And I will let you read the paper. It's going to be one of the things that you can see. You can get bonus credits for. Okay, maybe this is a good time to take a break. What do you think? Okay, let's take a 12-minute break. Let's come back at 57, and we're going to continue with routing. No, I think we'll start. We can meet after. Let me see. Are we still connected? Can people still hear me online? Hide something. Loading meeting controls. That's good. Okay. Okay, let's get started. So we're going to talk about routing now. We talk a lot about topology. We could keep talking about topology, but hopefully you got the basics. There's no end to topology. We will talk about topology toward the end of this lecture also. Because interesting thing happens when you combine topology and routing and buffering and flow control. So let's talk about routing. So routing is essentially, there are different types of mechanisms for routing. Arithmetic, source-based, and table lookup-based. I will not dwell into these a lot, but basically you can use simple arithmetic to determine the route in regular topologies. We will see dimension order routing in meshes and torus or tori. You could do source-based routing. Source specifies the output port for each switch in route. So that's another possibility, right? Because if you have a regular routing mechanism, or even an irregular routing mechanism, irregular topology where you discovered what the topology looks like, and you can basically specify whenever you inject a message, you can say, this is the path you're going to take, right? This is source-based routing. Circuit switching is kind of a version of it, not exactly, but circuit switching essentially says you set up the path. In that case, you don't even need to inject the path, inject the route into the packet you're sending, right? Table lookup based essentially is what's employed in dynamic packet switch routers normally. You basically index into the table for an output port. That's it's especially useful when you don't want to use arithmetic routing, for example, when you want to be more flexible than arithmetic routing. So source-based routing enables simple switches, just like static routing. There's no control state. You strip the output port of the header of your packet, and it basically tells you which output port you want to actually take to be routed to. Again, contention is a different issue. In contention, even though there may be two packets that want to go to the same output port, and the router may decide, okay, only one of them takes that one, and there's a prioritization mechanism that needs to happen in the router. So we'll talk about contention later. This is just basically how do you determine the route you want to take, right? But if you do source-based routing, it's usually a large header, unless you do, of course, circuit switching, right, where you don't have any header. And then you can do table lookup based. Here you don't have a large header, but more complex switches. Your switches need to basically determine the route using tables. Okay, I mean, this is simple, I think. But routing algorithm is a lot more interesting now, basically. There are three types of routing algorithms. One is deterministic. Deterministic routing algorithm always chooses the same path for a source and destination pair. We're going to look at that. Oblivious means you can choose different paths without considering the network state. And adaptive means the routing algorithm can choose different paths and it considers the network state, like the contention in different parts of the network, for example. And people have developed many, many routing algorithms. These routing algorithms can be used with any type of routing mechanism in the end. Okay, so how do you adapt becomes a question if you're adaptive. Do you take into account local feedback or global feedback in the network? For example, if you're going from this place to this place, how do you know whether there's congestion somewhere around here so that you can avoid that part, right? So there's a lot of interesting issues. It's not unlike determining directions in a map. It's not that hugely different, basically. You can collect some information and feedback that information to different parts of the network, and different parts of the network may be aware of the local or global congestion levels in different parts of the network. And then you can potentially take minimal paths or non-minimal paths. We're going to talk about that. Minimal path is basically the minimal distance between a source and destination pair. The question is always, do you always take the minimal distance, or can you somehow take non-minimal path, basically? Take a longer route so that you can avoid some congestion, for example. Okay, so we're going to talk about that also. So let's talk about the deterministic routing mechanism a little bit. Essentially, in deterministic routing, all packets between the same source-destination pair take the same path. One example is dimension order routing. And this is, I guess we can quickly look at this. Oh, maybe I'll look at this one. It's closer to me. So this is usually used in mesh type of topologies or torus topologies. And the idea is very simple, basically. You take the X dimension first and then traverse the Y dimension next. It's called also XY routing. A version of it is called YX routing, of course. Okay, let's remove this till something is happening. And then let's stop sharing. Is it looking good? Okay, so in a mesh topology, you basically have a bunch of nodes, and it's a two-dimensional mesh. Okay, we should have fetched or prefetched some of these things. I may use that. So basically, if you're going from this node to this node, XY routing says you first traverse the X dimension, and then you next traverse the Y dimension. That's how your packets get routed from source to destination, basically. So each router can simply calculate where it needs to forward the packet based on this principle, right? And then the results may be sent back. So maybe, for example, you're sending a message to the cache over here, and the cache is sending the cache block back, and the cache block may be sent with YX routing, like this. So this is the XY, and this is the YX. You can see that the route calculation is very, very simple, right? If you're getting a message from the left, you need to pass it to an output port over here, not here, basically. This doesn't go this way. A message coming from here is going this way. So hopefully this is kind of obvious also. It's very simple. Here, the routing decision is very, very simple. The router itself can still be dynamically switched, right? Because there may be multiple messages coming from, for example, there could be another message coming from here that is going to this way or this way, right? You also use the YX routing in this particular case, right? Okay, so let's go back to this. And this is used in many real systems. Oh, something is happening. I don't know why that's not happening easily. This is used in many real systems because of its simplicity. And you can see that Cray T3D used it. I already said this. We'll talk about deadlock. Basically, this is deadlock free, as we will see later on. There's no cycles in resource allocation, but I'll defer that for later. Deadlock is going to be an issue, basically. If you don't have, for example, some resources available, and if you don't do the routing right, then you may actually run into deadlock because nothing basically progresses in the network. And this actually is an issue that you need to deal with. It could lead to high contention. Well, going back to this picture over here, sorry. Essentially, it doesn't exploit the path diversity. That's the reason why it could lead to high. Okay, that's annoying. There should be a better way of switching between these things, like as opposed to stopping sharing, right? So this node is sending a message to this node, and all of those messages go through this path, right? If this node is also sending a message to this node, let's say, it'll also route through this path. If another node over here is sending a message to this node over here, it'll also route through this path. So everybody goes through XY dimension, and it basically leads to huge contention, while a lot of the paths over here are underutilized. Basically, this sort of deterministic routing almost always underutilizes your network. I mean, of course, there may be other ways of utilizing your network, like everybody here is communicating also, but we're assuming that that's not always the case. Basically, you're not exploiting the path diversity. There are a lot of paths over here that you could take. You could actually go this way, right? Who said that you go this way only? Basically, this is less deterministic, clearly, right? Depending on the contention you route. Okay, so hopefully that's clear. That's a big disadvantage of this sort of routing algorithms. Now we need to go back. Oh, how did we go here? Okay, does not exploit path diversity, basically. Now let's talk about deadlock in this, and I'll use this figure. Basically, deadlock means no forward progress, and it's usually. Wait a second. Is it working? No, do people see? I shared, right? Okay. Okay, deadlock means basically it's usually caused by circular dependencies on resources. And one example over here is that each packet waits for a buffer occupied by another packet downstream. So this example from a paper that I will mention next, it's a very seminal paper, shows the issue basically. So for example, this packet over here is supposed to go this way. Oh, okay, this packet here is supposed to go this way, but it cannot be allocated the buffer because it's occupied by another packet, which is supposed to go this way, but it cannot be allocated this buffer because it's occupied by another packet, which is supposed to go this way, but it cannot be allocated this buffer because it's occupied by another packet, which is supposed to go this way, but it cannot be allocated the buffer because it's occupied by the first packet that we started with. Basically, there's a circular dependency that you have over here that created the deadlock, because you have a circular dependency of resources on the packet. So none of these packets can get scheduled because of that. So this can be avoided by the design of routing algorithm, but it also can be avoided by other things like over here. But basically, you can avoid this sort of cycles in routing. The problem here is you're going, if you only had XY routing, XY, you wouldn't run into this situation, basically. You wouldn't go YX, basically. Some of these packets are going the other way around, if you will. So essentially, if you do dimension order routing, you cannot build a circular dependency. Essentially, this is a way of restricting the turns each packet can take. I'm going to talk about this next. But you can also avoid deadlock by adding more buffering, or like escape paths. If something like that happens, you have some special paths where you put the packet, and that's also been employed. We'll talk about that very briefly later. Or you can somehow detect this and break the deadlock, right? Somehow you detect that there's no forward progress that has happened in the past 100 cycles. What's going on? Let me deallocate one of the packet buffers, right? So that's a heavy-handed solution potentially, right? But ideally, you don't have deadlock in your design. And people have looked at this a lot. Basically, this paper introduced a turn model for adaptive routing. And the idea here is to analyze directions in which packets can turn in the network and determine the cycles that such turns can form and prohibit just enough turns to break possible circular dependencies. And if you really want to know more about it, you can read the paper. But essentially, XY routing ensures that. XY routing is one sort of deterministic routing mechanism that ensures that there are no circular dependencies based on this turn model. But it's not the most efficient one. Basically, you can actually make it much more efficient by following the methodology that's described in this paper. And again, I don't have time to go over it, but there's a lot of interesting stuff to discuss. Okay, so let's talk about, that was deterministic routing. Actually, this turn model applies to many other routing, but deterministic routing mechanisms and also adaptive routing mechanisms have issues with deadlock. And as a result, people have actually looked at this a lot. So we were talking about deterministic routing. If you go back over here, there are 3 different typing methods, routing algorithms, deterministic. Now let's talk about oblivious. So deterministic, we said, it's not that great because it doesn't exploit path diversity, right? Well, there's another routing algorithm that's almost completely at the opposite end. Basically, this is also called Valiant algorithm. That's one of the first algorithms, and you can read the paper related to that. Here, the goal is to exploit the path diversity, basically balance the network load. That's the major goal. If you have this huge network, why are you keeping some parts of the network unutilized or underutilized? Try to balance the network load across all of the links. And to be able to do that, the idea is to randomly choose an intermediate destination and route to it first, then route from there to destination. That's the idea. Between source and intermediate to destination, you can actually use dimension order routing. So this is actually an interesting idea. Maybe we can also take a look at it very quickly with a lot of overhead of switching. So I'll try to use the same picture. Let's see how well it'll happen. So basically, you can actually divide the network. Okay, maybe I will not use the same picture, but then I don't know. Can you see still? Okay, good. So this is your network. You divide into, let's say, quadrants. And let's say you want to communicate from here to here. You don't communicate directly from here to here using XY routing, but you basically first randomly choose some other quadrant. Let's say one of these. You choose this one, and then you send a message randomly here and then to here, right? It's a random node that you select, not necessarily one node over here. So the basic idea is to distribute the load as much as possible. And then maybe some other node, this node over here, sending a message to this node. It randomly chooses some node over here, it sends a message over here, and then from there to there. Each of these messages can be routed through dimension order routing. Now you can see that everybody is randomly choosing some node from some other quadrant and sending a message there. As a result, you're really balancing the network load across the network. And this is clearly good for balancing the network load, but it doesn't look like very good for latency, right? You first go through some intermediate node, and then from that intermediate node over here. Right? So if you really want to utilize your network, this is not a bad idea. But for your latency, it doesn't sound great. Okay. Okay. So as I said, between source and intermediate destination, you can use dimension order routing to ensure that you don't have deadlock, etc. Right? And the upside is to randomize or balance the network load. The downside is now packet latencies can increase. It's actually quite non-minimal. So basically, you've given up on the minimal path in this particular case by design. But of course, there are cases where this could be useful, right? And for example, when you have very high load on the network and some parts are not utilized, you can do this on high load. You can restrict the intermediate node to be close and potentially in the same quadrant. So you can actually change the way. I just showed you a potential implementation of this. So there are cases where this could be actually useful when your network is not very well utilized. So if you always do dimension order routing, for example, deterministic routing, depending on your access pattern, there are parts of your network that's going to be not very utilized. So you can actually use this to increase the utilization of your network. So you can actually combine the mechanisms as well. Okay, if you want to know more about this, these are actually seminal papers by Leslie Valiant, actually, who's a Turing Award winner. In terms of, because he's one of the inventors of the bulk scalable processing paradigm, or bulk synchronous parallel processing paradigm. Okay, so let's talk about adaptive routing. Adaptive routing is essentially trying to be a little bit more intelligent, let's say, compared to both. And the idea is to use the network state somehow to decide what route to take. And there are two versions of it. One is minimal adaptive, and the other is non-minimal or fully adaptive, if you will. Minimal adaptive means you always try to take the minimal route. Router uses the network state, for example, downstream buffer occupancy, to pick which productive output port to send a packet to. So what's the productive output port? Productive output port is a port that gets the packet closer to its destination. So this exploits path diversity. So what does this mean? Basically, there's not a single productive output port. Sometimes there are multiple productive output ports in a path, right? Because remember the definition, port that gets the packet closer to its destination. So let's take a look at an example over here. Again, stop sharing. Okay, I'll use this one. So for example, your goal is to go from here to here. You can take this route or this route, right? So there are two productive output ports here. And there are two non-productive output ports. So minimal adaptive basically makes a choice between these. You can go this way or this way. And that choice may be based on, oh, there's some congestion over here, so I'm going to take this path, right? That's the idea. Now, once you start taking these ports, you're non-minimal adaptive. And it's clearly fully adaptive. Now you can exploit the full path diversity in the network. But that causes some other issues, as we will see, right? Minimal adaptive enables you to always make forward progress. Whereas non-minimal adaptive starts the danger of maybe you're never making forward progress, right? Because you can keep circling around the network without getting closer to your destination. Whereas minimal adaptive, you're always getting closer to your destination, right? So that's the difference between minimal and non-minimal adaptive. Even although non-minimal adaptive is actually much better for network utilization, as you can see. Okay, let's go back. Okay, so basically, non-minimal, I just described it. You can misroute the packets to non-productive output ports based on network state. Misrouting means you send the packet to a port that it's really not going to, it shouldn't really go to, assuming you're taking a minimal path. Okay, so minimal adaptive is aware of local congestion. I mean, you could also make it aware of somewhat global congestion also, but you have limited choices, as I said, right? You have only two choices in the mesh, for example, in that particular case. In some cases, you don't even have two choices, right? Minimality restricts the achievable length utilization or load balance across the network clearly, as we showed. Now, with non-minimal or fully adaptive, now you can achieve better network utilization and load balance because now you can fully exploit all the paths that are available to you. You don't care whether you get routed farther away from your destination. Now, the downside, as I said, is how do you ensure that you actually get to your destination, right? You need to make forward progress. And this now creates an issue called live lock, meaning a packet may be always moving around the network, but not making progress to its destination, right? It may never reach its destination if you don't have mechanisms to provide live lock freedom. So this is interesting. Now we kind of turned the problem. Actually, usually non-minimal adaptive mechanisms turn the deadlock problem into a live lock problem. So if you're actually doing things right, if you're fully adaptive, you should not have a deadlock problem because you should always route around things. But now we have a live lock problem. Okay, so this adaptive routing is actually very useful, and I think it's necessary because, especially in the presence of faults, because this enables you to avoid faulty links or routers. And the idea is to route around faults, because deterministic routing cannot handle faulty components, right? If you have a deterministic route and one of the components in the middle fail for whatever reason, you have to route around it, right? How do you route around it? Now it's not deterministic anymore, your routing. Well, I guess it could be deterministic, but it's not. Now it becomes a different routing algorithm in the end. And you need to change the routing table to disable faulty routes, essentially, assuming the faulty link and router is detected, which is another issue also. So there are many interesting things over here. This is a work that we have done. There are a lot of interesting problems over here, but I'm not going to talk about this. So fault tolerance and guaranteed delivery actually leads to other issues. Yes. Yeah. Yeah, maybe. I mean, I don't know for sure. Basically, I guess it depends on what kind of security issues. Are they security issues like someone can change the routing tables, or? Mm-hmm. No. Yeah. I mean, this paper actually talks about a lot of those things. Basically, if you have faults, how do you ensure that you have guaranteed delivery? Not from a security perspective, though. I guess the security is an issue if somehow somebody figures out how to change those routing tables without having the right privilege, right? That's what you're thinking about, I think. Yeah, if that's somehow done, if that's somehow doable, of course it will be a security issue, of course, right? Yeah. Okay, but a lot of the things that you discussed is actually, are you actually reachable to your destination becomes a problem when you have faults. Yeah. Okay. Okay, that's about routing. We can talk a lot more about routing, but we don't have time. Again, if you want to know more about routing, you can read the principles and practice of interconnection networks. But beware that that's from 2004, right? We're in 2022. Yes. So this routing algorithm is, it's happening in the router itself, the switch, and the switch is deciding to, switch is deciding which output port to send the packet to. The packet could be a data packet, control packet, doesn't matter. It's just a message or a piece of the message that you're sending. But you're deciding which output port should it go to. I mean, yes. It could be pre-decided also, right? That's another decision, right? So certainly you can decide it statically as well, right? But I think a lot of the things that we're discussing right now over here is at every point in time, right? This router, especially the adaptive routing algorithms that we discussed, are you get a packet from this. The question is, and it needs to go to here, for example. Do you send it this way or do you send it this way? So it's basically when you get the packet dynamically. You can think of it as every time step, yes. Exactly, yes. Every router implements this routing algorithm. I mean, yeah, you can think of it that way. I guess depends on the definition of intelligence, but yes, every decision is made across the routers. Mm-hmm. Mm-hmm. Yeah, I mean, this is a dynamic system, right? Basically, anyone can be injecting a message to any router in the end. Yeah. Yeah, basically, the decisions are all made dynamically. Okay. Okay, so let's talk about buffering and flow control, which is going to take some time, and it's important. So let's recall circuit versus packet switching. We discussed this actually. We said that circuit switching requires no buffering, whereas packet switching requires some way of handling contention, and usually it's done via buffering. But it's not necessary to do via buffering also. And we discussed that actually circuit switch networks exist and they don't have buffers in this particular case. So I'm going to skip this, but packet switch networks have some packet formats. That's not so interesting. You may have seen this in your networking course. But maybe I'll discuss because I'm going to talk about header later on. So header means you have some routing and control information. And payload means whatever comes after, the message basically. And it can carry data, it can carry some coherence message, for example. And then there could be some error code, as we briefly mentioned, to make sure that this could be a checksum of the message, for example. When it's received, the receiver computes a checksum and checks whether that checksum matches the checksum over here to make sure that there is no, it's essentially an integrity check of the data. There are no errors during transmission. So this is a potential packet format. It's used in many systems. This will be useful for later, so keep this in mind. But let's talk about handling contention. So buffering and flow control are really about handling contention. And essentially, you have a router that looks like this, and two packets. I don't know what happened to these colors. Yeah, they don't look very good over here. They look a little bit better over here. Interesting. But basically, there are two packets over here. One is arriving from the top. It's trying to go over here. The other arrives from the bottom and it's trying to go over here. And they're trying to use the same output port or same link at the same time, right? So what does the router do at this point, right? There are three choices, actually. It could buffer one of them, right? It could send one of them this way and stop the other one and wait. That sounds good, right? It can drop one of them. Now, this causes some issues, right? If you buffer one of them, this causes deadlock type of issues, like we discussed. Basically, all of them have issues in the end. If you buffer one of them, you need to have a buffer, and you need to ensure that there are no deadlocks. If you drop one of them, you need to ensure that the thing that's dropped, the source node that sent the packet gets informed about this, right? Or they somehow infer this. So there's a problem over here, but this is one way of handling contention. Or you can misroute one, as we discussed, right? Which in non-minimal adaptive algorithms, basically, you say for example, the top one, you take your productive output port, bottom one, unfortunately, you have to go through a non-productive output port, assuming this is a non-productive output port. So go and take some other link. So these are three fundamental choices in handling contention, and they all have implications on router design, router efficiency, as well as the entire network design, because the implications are actually, for example, if you drop one of them, now you have an implication across the entire network, right? You need to basically send a message back to the source whose packet was dropped. That's one way of handling it. And you still need to, so dropping also converts the deadlock problem into a live lock problem, right? How do you ensure that not just this packet, but this high-level message that was generated by the source that's probably going to be generated again makes progress? So that's a live lock problem now. Misrouting one also turns a deadlock problem into a live lock problem, because now this packet is misrouted. How is it going to reach its destination? And if you have a lot of contention or congestion in the network, this may keep happening and no packet may reach its destination in the end. So this live lock problem can be serious, actually. So there needs to be some ordering of the packets so that you can actually ensure that one packet always reaches its destination and every packet eventually reaches its destination. Okay, so these are some trade-offs that I kind of discussed. We're going to look at these trade-offs, especially next week, more. But let's talk about some flow control methods right now. Any questions on this? This slide is a very fundamental slide in the end. And you can also combine these things. There's no reason why you choose only one, right? You have some buffering. When your buffering runs out, what do? Maybe you start dropping, or you start misrouting, right? You can actually combine all of these at the same time. And there are actually designs that have combined them. Because you may not want to have lots of buffering because that's expensive, right? Now your routers are huge. And that was one of the motivations in Huawei's design, for example. They didn't want to have this huge area in their buffers. And they wanted to actually go bufferless, let's say. That was exactly our motivation, actually, when we proposed the bufferless network on chips. We will discuss that. Well, one of the motivations. There are many motivations, I think. But that's one of the motivations. But misrouting is called deflection routing. Also, basically, you're deflecting the packet. It's also called hot potato routing. This was actually an old idea that was proposed. All of these date back to the 1960s when people were designing distributed communication networks. And hot potato means basically each router gets a packet. And packets are things that you cannot hold, right? It's too hot. You have to basically send it somewhere. And send it anywhere. It doesn't matter where it wants to go to. Of course, if you have a productive port, send it to the productive port, but you cannot keep it. You cannot buffer it. Okay, so think about the trade-offs over here. So let's talk about some circuit flow control methods. So there's circuit switching, we discussed. There's bufferless. Bufferless doesn't need to be circuit switched. Basically, circuit switching actually enables bufferless. You could actually add buffers over there for whatever reason, for, I don't know, rate control, for example. But you can actually have bufferless routing or deflection routing with packets. And then there are a bunch of packet-based flow control methods that we will look at in a little bit. Let's talk about circuit switching. So in circuit switching, resource allocation granularity is actually very large, right? Essentially, you're allocating all of the routers, all of the paths along between a source and destination pair. I mean, I've given you the idea over here. Pre-allocate the resource across multiple switches for a given flow. To be able to do this, you need to send a probe to set up the path for pre-allocation, as we discussed. But this eliminates the need for buffering. There's no contention. Flow's performance is isolated. Okay, assuming that you've allocated all the switches, this flow's performance is isolated because only this flow can use those switches, right? At least the output ports. When I say switches, I should say really the output ports of those switches. And this can handle arbitrary message size. As I said, if you want to transfer 1 terabyte of data, you set up the circuit once and you keep pumping the data. And the routers don't consume any energy because they're pre-configured. Right? So in terms of energy efficiency of sending large amounts of data, circuit switching is great. But as I said, this cannot handle concurrency very well because the output port is dedicated to only one flow. 2 flows cannot use the same link, essentially. And there's a handshake overhead to set up a circuit. Okay, let's talk about bufferless. The key idea over here is packets are never buffered in the network. When 2 packets contend for the same link, one is deflected. I like using a picture like this. So let's say both of these packets need to go to this destination. They arrive at this router. Clearly, they both cannot take the productive port. This is the only productive port for both of them, right? You cannot send it to any other port and keep the minimal path. So one of them takes the, let's say, scenic route. And it turns around and eventually gets to its destination, hopefully. So clearly that this particular packet, the blue one, took longer, but now you eliminated the buffers. So this routes around the congestion areas. And new traffic can be injected whenever there is a free output link, as opposed to relying on buffers. So this is very similar to the buffered crossbar that we discussed. Whenever you are injecting to a shared destination node, shared destination link, you need to ensure that there's a free output link in a crossbar also. Okay, so basically, if you look at a modern router, which we will discuss again next week, a modern buffered router looks like this. You can have input buffering, you can have output buffering, you can have both. If you really want to know about all of those details, again, read the book that I mentioned earlier. A lot of existing systems use input buffered routers, but output buffering is also interesting. These have implications on router designers, actually, basically. How do you actually allocate things? How do you do the arbitration? They all depend on whether you have input buffering or output buffering. So there's a lot of interesting stuff that you can do in the design. But I'm going to assume input buffered routers. So here, basically, you have a 5-to-5 crossbar, as you can see, and you buffer some things. And we're going to introduce what these means later on. Don't worry about that right now. Essentially, packets are buffered here normally. But with the bufferless routing, you eliminate all those huge buffers, essentially. You basically turn the problem of buffering inside these dedicated buffers to buffering in pipeline latches, which are not shown over here, and network links. So what you're doing over here is, if you think about it, instead of buffering one of these packets, you're using the links as temporary buffers, right? Temporary places that packet goes to. So that's the idea, basically. So clearly, links provide a limited amount of, let's say, capacity handling. Okay, so there are a bunch of issues, and we will talk about that next week, some of these next week. Live lock is a big issue over here. How do you handle that efficiently? Router complexity actually is not that simple. So this picture is not that simple, unfortunately, because you need to handle live lock. And because of that, router becomes a little bit more complex, but you can eliminate that complexity. and performance and congestion at high load. So one of the big benefits of buffers is the different sources can keep injecting into the network, into this router, for example, and you keep handling that load, right? If you don't have these buffers now, you resort to only links, and those links are not that many, because clearly there are only five of these links, right? Whereas here, buffers, you can add, I don't know, 1,500 buffers, right? You can keep 1,500 things over here. So basically, you can absorb a lot more load if you have buffers. But if you don't have buffers, then you have some issues of congestion and performance at especially high loads. So we're going to talk about this paper. So there's a lot of work in actually bufferless deflection routing. And we're going to talk about a bunch of papers next week. And as I said, this is the hierarchical rings, actually. I think in the end, it's good to, as I mentioned at some point, it's good to do the extreme study. What happens if you get rid of all of the buffers in the system? It's good to understand the potential of that. But in the end, getting rid of all of the buffers in the system is a very extreme approach, in my opinion. It's really, you really need to have some sort of buffering to manage things. And that's what these papers argue, essentially. For example, this one introduced minimally buffered deflection routing. And this one actually looks at topologies, like hierarchical ring topologies, that can use deflection routing in a way that combines bufferless and buffered rings. And you can take a look at that. Okay, we can see more. Okay, and this paper actually is inspired by these works as they discuss, and they have a bufferless hierarchical ring essentially. Okay, so let's go back to buffers right now. So buffers actually complicate things. I'm going to discuss some of these buffered flow control methods, and they're all going to complicate things. But before we move on, any questions? Okay, no question on bufferless or deflection. Such an intuitive and nice idea, right? Okay, you will see more about that next week. So let's talk about how do you do flow control and buffering in essentially buffered networks. So we're going to look at packet-based flow control. One very simple approach is store and forward. It's not employed in existing systems, but basically the idea is store the entire packet into a router before moving anything, any part of that packet to the next node. So flow control unit is the entire packet in this case. So a flit is equivalent to a packet, basically. In this case, there's no distinction between a flit and a packet. So if you look at the source and destination over here, this is how the routers behave. Source initially has the entire packet. Well, I'm going to talk about that after I show you the picture. Basically, what happens is it sends the entire packet to the next router. Once the next router receives the entire packet, it can start sending the piece of the packet to the next router. So you can clearly see that this doesn't sound very good because you're not pipelining pieces of the packet across different routers, right? So as a result, this leads to high power packet latency. And it also has a high buffering requirement. It requires buffering for entire packet in each node. So if your entire packet is, I don't know, 512 bytes, then you need to have that buffering. But maybe you want to be frugal and you want to buffer only pieces of the packet, right? So this is store and forward. It's a very simple and primitive method. Now, it's also good to think about the packet granularity and the link transfer granularity. Here, I'm assuming that the packet granularity is larger than the link transfer granularity, which is almost always the case, especially for cache blocks, right? Cache blocks are very large. It could be like, let's say, 128 bytes, and your link granularity may be only 64 bits, right? So basically, you need to send pieces of the packet. So people have realized that this is actually not that good. So can we do better? So they've invented different flow control methods. Cut-through flow control is another form of packet-based flow control. You start forwarding the packet as soon as the header is received, and the resources are allocated downstream. I'm not going to talk a lot about resource allocation and how it's done. Again, you can read the book. There's a lot of interesting issues over here in router design. We're going to talk a little bit about that next week, but not in a lot of detail. But basically, this leads to large reduction in latency. Let's take a look at how this is done. Yeah, as you can see now, you can actually pipeline the packets a little bit, right? So whenever you receive the header and allocate resources downstream, you can send pieces of the packet. So a packet can be distributed across different routers like this. So this leads to a large reduction in latency in the end, but it still allocates buffers and channel bandwidth for full packets because in the worst case, this actually at least degenerates into store and forward. So what if packets are large? Again, you have huge buffering resources that's needed. So basically, in cut-through flow control, the reason why you need to buffer the entire packet is what do you do if the output port is blocked? Okay, let me define maybe head and tail. So if you look at this, this is the head piece of the packet, and this is the tail piece of the packet, and the rest is the body, right? So basically, you cut-through flow control lets the tail continue when the head is blocked, and it absorbs the whole message into a single switch. As a result, it requires the buffer large enough to hold the largest packet. So essentially, it degenerates to store and forward when you have high contention in the network. So this helps a little bit average latency, but this doesn't help the worst case latency. So people ask the question, can we do better? And people have invented what's called wormhole flow control. And the idea here is much nicer, let's say. Packets are broken into potentially smaller flits, usually smaller flits, because if you have a large packet, usually it's more than one flit. And now flit is the buffer and bandwidth allocation. So in the previous cases, packet was the buffer allocation unit. Now we're going to actually reduce the allocation unit to a flit, which is a smaller piece of the packet, flow control unit. Okay, let me go back. And flits are sent across the fabric in a wormhole fashion. So if you look at this picture over here, this picture shows that you have the head flit over here, and you just need resources just for one flit, for example. You have the body flit over here. You just need resources to allocate that one, another body flit, and a tail flit. Basically, you can get away with very frugal buffer resources for a given packet in each router. You don't need to allocate the entire packet in each router. And it's called wormhole because you can see that it's like a worm, right, across the network. You have the head of the worm over here, body of the worm, and the tail of the worm. And they can basically take different paths also. They can basically essentially go around based on how they're routed. Okay, but the routing within a single packet is essentially determined by the header. So body follows the head and tail follows the body. And essentially this allows complete pipelining, which was allowed using cut-through flow control, but now your resource allocation at the granularity of a flit also. And if the head is blocked, the rest of the packet stops. So the packet is still a single unit, if you will, but the buffer allocation is done at the flit level. And this also enables, one of the reasons is you have routing information only inside the header flit. Basically, you have a single packet, you break it into flits, but the routing information is only in the head, right? So if you actually broke it into, if you had routing information in each of these, those would be packet by themselves, if you think about it. Okay, so I think you may need to digest this a little bit, but so how does the body or tail know where to go? Essentially, header flip sets up the router. It follows the head. So there's some state in the router that is set up by the header flit that identifies a packet saying that I'm the header flit, and if you're the body flit belonging to me, you should go this way, right? And now the latency is almost independent of distance for long messages. If you have a very long message, you keep pipelining it across the routers. Of course, this is dependent on the length of the message. If you're a very short message, your latency is, of course, not like this. But if your message is 1 terabyte, let's say, and if your flits are 64 bytes, well, 8 bytes, let's say, then basically your latency is independent. Okay. Whereas that's not the case in cut-through or store-forward. Cut-through and store-forward requires basically a lot of the entire packet to be allocated. Okay. Any questions? Okay. I mean, hopefully the advantages are clear over store and forward. You have lower latency and more efficient buffer utilization, but it still has limitations, and people have attacked those limitations. It suffers from what's called head-of-line blocking. Basically, if head flit cannot move due to contention, another worm cannot proceed even though links may be idle. And I will demonstrate this in a little bit. And this is a simple example, basically. You have these 2 input links and then 2 output links, 2 by 2 crossbar. This is a switch, basically. And these are the flits. These are the outputs that these different packets want. 1 or 1 over here, basically. So if you look at this, what's happening is the heads over here both want the output port 1. Unfortunately, only one of them can take it, right? Now, one of them will be prioritized. Let's say this one is prioritized. This one will wait in the buffer. But this becomes idle, right? So essentially, the problem is because we have a single queue and we're doing the arbitration by looking at the heads of those queues. You have what is called the head of line blocking. This packet over here wants to go to output port 2, but it cannot go to output port 2 because it's not arbitrating. What is arbitrating is the head of these queues over here. So this leads to lower link utilization. Of course, I mean, this problem can be solved by arbitrating, by looking at all of the possible head flits in all of the possible packets that are inside the queue, and then deciding which one should take the output port. But that's very complex also, because imagine that you have actually lots of input queues. I mean, it's done in actually existing processors, right? You have auto-order execution, which enables something like this, but the complexity in the routers actually can be, we don't want everything to be as complex as auto-order processors. And there's also another mindset, if you will. People didn't think about making things completely out of order over here because they wanted to be frugal in terms of resources. So this is called head of line blocking. I'm going to illustrate this again. Basically, a worm can be before another in the router input buffer, just like I showed you over here. And due to the FIFO nature, first in, first out nature of the buffer, each of these queues, the second worm cannot be scheduled, even though it may need to access another output port. That's what we have seen over here, right? The second worm over here cannot be scheduled, even though it can use this output port that's otherwise going to go idle, right? And that's the idea of head of line blocking. Now let's take a look at how this impacts the entire network. So let's assume that this link is blocked by other packets for whatever reason, for some busyness over here. And these blue packets, this blue packet wants to go to this destination, and this red packet wants to go to this destination. Let's take a look at what happens. So wormhole fashion, you send the flits. Now this buffer becomes full, so this blue packet cannot proceed. So it occupies the FIFO over here. Now what happened is this red packet cannot proceed because it's behind this blue packet over here. Even though this output port is idle, this poor red packet got stuck behind this blue packet in the FIFO queue, right? That doesn't sound very good, right? This is the downside of FIFO scheduling, if you will, first in, first out scheduling, where you just look at the heads of the queues. Okay, so this doesn't make sense, if you will, but it does make sense if you actually design things the way that I just showed you over here. Basically, if you just check the heads of the input queues to decide which output port should be allocated, you're not checking what comes behind the head of the input queues, right? Now, what's happening over here is the blue packet is really blocking the red packet, which is going through a complete different route. So this leads to a lot of congestion in the network in the end. And red packet also occupies this channel because it has nowhere else to go over here, as you can see. And that channel is allocated to it because it's a wormhole flow fashion. So it has implication downstream also, if you will. So there may be another packet that wants to go this way, but it cannot go this way because red packet is actually occupying that channel. So this sort of scheduling issues that are not, let's say, suboptimal, that are suboptimal, lead to congestion in the entire network. And that's the realization with head of line blocking. And this is a seminal paper that basically realized this issue and developed a very simple solution. And that's the idea is called virtual channel flow control. Unfortunately, I think you can see that the terminology now actually grows and grows. That's a bit unfortunate, but that's how it is. This idea is used, this terminology is used very heavily across a lot of, let's say, communities. But the idea is to have multiplex multiple channels over one physical channel. I'm going to show you how it's done, basically. You divide up the input buffer into multiple buffers, sharing a single physical channel. So it looks like this. Instead of having an input buffer that looks like this, a single queue, have multiple queues over here, and then arbitrate between the heads of those. And if you keep increasing the number of queues, it's called virtual channels over here, then the probability of head of line blocking reduces, essentially. And if you steer different worms to different virtual channels, certainly the probability of conflict across different worms reduces. Of course, there will still be a probability of conflict if two different worms go to the same channel, right? So that's the idea, basically. Now, the upside of this is you don't do out-of-order scheduling within something over here, but you need to look at more heads of each of these queues over here. Okay, basically, this is the idea. This is from the paper. As opposed to having a 16-flit FIFO buffer, you have 16-flit 4-lane 4 different buffers, and you arbitrate between the heads over there. Different worms go to different buffers over here, if you will. And these are called channels, essentially. That's where the virtual channel comes from. I'm not a big fan of the terminology, unfortunately, but it got stuck. It's stuck very well in the community. So you need to get used to the terminology, basically. But the basic idea is very simple, as you can see. As opposed to having a single queue that houses multiple different worms, have more queues that hopefully house fewer worms each. And this reduces head-of-line blocking. So basically, if you have 2 virtual channels, now we're looking at the same picture with 2 virtual channels, right? Different worms get allocated to different channels. Assume that the same thing happens. This is blocked by other packets for whatever reason. Now the blue one keeps going into its virtual channel. At some point, its buffer becomes full, so it cannot proceed. Fine. But now the red one can proceed because it's going through a different virtual channel, and it can be scheduled independently of the blue one because its flits don't get stuck behind the blue one. So this is a method of keeping the simplicity of FIFO queues while getting some part of the benefits of out-of-order scheduling. But if you're not going fully out-of-order scheduling, you're still examining just the head of the queues when you do the scheduling in a router. But complexity is, of course, higher than a single queue. Hopefully that makes sense. And modern routers actually employ this sort of virtual channel. So this is a virtual channel-based router, modern. And you can see that these are input channels or input ports. These are output channels or output ports. And the reason it's called virtual channel is because this is thought of as a physical channel, but then there's a virtual channel over here where physical channel actually gets divided into multiple different virtual channels. That's the idea. That's the reason why it's called virtual channels. Yeah. Unfortunately, we cannot change that terminology at this point. But basically, different worms go into different virtual channel buffers here. And the hope is that they don't conflict with each other. The hope is that you won't get contention between different worms. But again, that depends on how many worms go to how many channels in the end. There's a design choice over here. So you can see that a modern virtual channel-based router actually is complicated. There's routing logic that's used. There's a virtual channel allocator actually that decides where should the thing that's coming go to. There's a switch allocator after that, which basically decides which input channel should be connected to which output channel, and within which input channel, which virtual channel should be connected to which output channel. So basically, there's a lot of scheduling that goes on. There's a routing logic that determines actually which, essentially based on the header information in each worm, which output channels are desirable for that particular worm. Right? So there's a lot of complexity actually, and there's a lot of buffering in a modern virtual channel-based router. And we're going to tackle that next week. Any questions on this so far? I've covered a lot of material. A lot of this is really fundamental and interesting, but it may not be easy to, let's say, parse through the terminology. But in the end, as I said, the fundamentals are very simple. Ignore all the terminology. What we're doing is basically, as opposed to having a single queue and arbitrating on the head of the queue, we have many different FIFO queues and arbitrating on multiple different heads. And hopefully by allocating different worms to different queues, you get rid of head-of-line blocking across different worms. Okay. Yes. Mm-hmm. When you say lots of a huge amount of data being transmitted from one source to another destination. Yeah. Well, I think again, circuit switching helps those cases, right? If one node is sending a message to another node, if you set up a circuit with lots of data, then you amortize the cost of switching across many amounts of data. Yeah. I mean, it doesn't apply to what we discussed, of course. These are not circuit switched, right? Clearly, these are packet switched. But circuit switching is a very efficient approach for those large data transfers. That's why in Tylera, for example, for streaming data, so I think what you're discussing is an example of streaming data. They've used a circuit switch network for those cases. Yeah, we talked about earlier when we talked about circuit switching versus packet switching. Yeah, you can take a look at that. Yeah. Okay, so virtual channels actually, people have introduced virtual channels for head-of-line blocking, But there are other uses of it. One use could be deadlock avoidance. So essentially, enforcing switching to a different set of virtual channels on some turns can break the cyclic dependency of resources. I'm not going to go into this in more detail, but you can break some of the deadlock or possible deadlocks. You enforce some ordering on the virtual channels. You can use escape virtual channels, meaning have at least one virtual channel that uses some deadlock-free routing, and the rest may be using some not deadlock-free routing, and ensure each flit has fair access to that virtual channel. So there are mechanisms to actually take into account. And then there's something called protocol level deadlock that we didn't discuss. Here, essentially, you may send a request, but you may never get a reply, for example, right? Because there's some sort of issue in the network such that some request packets always get delayed behind reply packets or vice versa for whatever reason, right? This can be resolved by ensuring address and data packets use different virtual channels, for example. And this prevents cycles due to intermixing of different packet classes potentially, right? Again, I'll go through this relatively quickly because we're not going to go into the details, but essentially different virtual channels enables you to avoid some of the deadlock related issues. They also enable some sort of quality of service. It can enable you to prioritize traffic classes. Some virtual channels may be assigned higher priority than others dynamically or statically. And that could be very useful, clearly, for prioritization. You could also use prioritization without virtual channels, but virtual channels certainly help because how do you do prioritization without virtual channels if you actually have a single queue, let's say, and there are a bunch of packets of different priority inside the single queue, right? If packets are of different priority, maybe you send them to different channels and then consider the priority when you do the arbitration of the heads of the FIFO queues. Okay, so I think we've already discussed this, so I will not go through this because we don't have a lot of time. But basically, what we've done is we started with store and forward. We shrunk the buffers and reduced the latency, which took us a wormhole, I should say, remove cut through from here. And then that led us to head of line blocking, and we solved the head of line blocking by using virtual channels, which we've already animated like this, right? And that's the state of the art, basically. So you can see that now we are adding buffering, a lot of buffering into our networks. Now, buffering also introduces some other issues. I will quickly talk about them. Okay, we have some time. That's good. It's interesting because how do you communicate buffer availability? So the issue is that this node is going to send a packet to a downstream node, a flit. How does it know it can send the message, right? It can send that flit because it doesn't know the buffer availability. If there's no buffer downstream, if you're assuming a buffer-based flow control, then you should not send the message downstream, right? So you need to communicate the buffer availability from a downstream router to an upstream router. An upstream router needs to have all the information about the buffer availability of potentially all other routers it can send a message to. And this is something that complicates flow control in buffered networks in general. And there are multiple methods. These are some example methods. We'll take a look at a few of them. And all of them require messaging, like back signaling from a downstream router to the upstream router. So it's not just, you cannot just decide to send a message to the next router. You have to check the availability of router in the downstream, availability of the buffer in the downstream router. And for that, there needs to be some message that gets communicated back to you beforehand. So credit-based flow control says upstream router knows how many buffers are downstream, and downstream passes back credits to upstream saying that you can send this many messages to me. And this requires significant signaling upstream, especially when you have lots of flits. So there's a lot of signaling that needs to happen because every time the downstream buffer, the downstream router makes one buffer available or not available, it needs to communicate that information. I mean, it doesn't need to be every time. It can be done at a coarse granularity. But once you go to a coarse granularity, you need to basically take into account the fact that there's some latency associated with sending messages. Okay, on and off flow control. Basically, it says, it's a bit, let's say, heavy-handed. Downstream basically says stop right now or continue right now. On and off signal, essentially. A bit simpler, but there are trade-offs over here. And you can read the trade-offs in the book. There's also ACK-NACK flow control. This is optimistic. It's similar to the optimistic concurrency we looked at, right? These two are pessimistic. Credit-based flow control and on-off flow control are pessimistic. Basically, you cannot send something. Here, you basically send a flit downstream, assuming that it will be buffered downstream. But the downstream router sends an acknowledgement or a negative acknowledgement, depending on whether or not it has availability of the buffer. Now, clearly, this is possible, but once you send the once you send the FLIT, you cannot get rid of it until you receive the ACK or NAC signal, basically. Now, certainly you cannot get rid of it when you have the NAC signal, but when you get the ACK signal, you can remove it. So the buffering actually increases this way. Okay, let's take a look at credit-based flow control. So we are looking at two, this is an upstream router and this is a downstream router. Node 1 is sending a message to node 2. So when node 2 actually makes one buffer available after it schedules a FLIT, it sends a credit back to node 1. And node 1's process, there's some processing time over there, and then it can send FLITs. And then once it sends a FLIT back, it sends a credit back to its upstream routers. And it's not just one router, it could be multiple routers, right? Okay, so think about this basically. There's significant credit signaling, as you can see. And then this processes the FLIT. So there's a credit round trip delay, as you can see over here, that affects the latencies over here. So this credit round trip delay actually leads to the buffering requirements. So here you have a FLIT that's departing the router, and you receive the next FLIT at this point in time, right? So there's a delay over here. So the buffering in the previous router is dictated by how long it takes from the time when a buffer becomes available and when the next FLIT to utilize that buffer is received. So this actually increases the buffering because there's some latency associated with it. So this is essentially, I already said this, but this is time between when the buffer empties and when next FLIT can be processed from that buffer entry. So this leads to significant throughput degradation if there are few buffers. If basically you don't have enough buffers to account for this credit round trip delay, then you can have significant throughput degradation. So usually the buffering buffer sizing is done in this sort of networks to account for this credit round trip delay, assuming you're using credit-based flow control. So I already said this basically. Important to size the buffers to tolerate this credit turnaround. Again, you need to think about this a little bit basically, because this is really about when do you allocate a buffer and when can you unallocate a buffer. And there's some time between that, and you need to take into account. So let's take a look at on and off. On and off looks like this. You send a FLIT, and node 2 determines that it doesn't have enough buffers anymore, assuming there's some delay, and you may be sending some FLITs still. So it basically says, okay, please turn off. But this turn off doesn't mean that I don't have any buffers available. This means that assuming that you are going to send some more FLITs to me, I will not have buffers available. Because I know that there's some latency from the time I send you an off signal until you actually get that signal and stop sending requests to me. So this is a bit, so basically there could be another FLIT sent in the meantime, right? So you can see that this happens. So this off signal needs to take into account the fact that upstream node may be sending FLITs, and there's a processing delay. So basically this threshold is set to prevent FLITs arriving before this time 4 from overflowing the buffers. So there's some conservativeness that's built in the buffering for that reason. Okay, and then you send some number of FLITs, and then there's an F1 threshold that's reached, and then you send an on signal. And that on signal also accounts for things, as you can see. Okay, and then this F1 is actually set so that node 2 does not run out of FLITs between T5 and T8. So you need to actually set these thresholds so that you don't basically stay idle during this period while this router is receiving an on signal, right? So the reason I said this was heavy-handed is because of this essentially. It's kind of heavy-handed because you need to take into account these delays of off and on signals, and then you need to allocate enough buffering to ensure that your throughput doesn't get degraded. It's just a similar problem to credit-based, but credit-based is much finer grained. Here it's a bit more coarser grained because you're saying basically stop. Okay, any questions? Again, there are more flow control methods, but I don't have time to go over them. And this is really a good time to stop because I was not expecting to get here and I didn't get here, interestingly. So next week, we're going to start with this load latency curve, which is going to be interesting. We've seen this actually earlier, but we're going to look at it from the perspective of interconnection networks. And then we're going to cover on-chip networks first on Thursday. So if there are no burning questions, we should stop here. And I'll see you all next week. Have a good weekend. Thanks.